Hello there, and welcome to Science for Sleep. Tonight we're turning our attention to one of the most puzzling and strangely slippery ideas in all of physics. We use the word casually in daily life, as if it's the simplest thing. We say we have nothing in the fridge, or there's nothing to do on a rainy afternoon, or that someone said nothing during a conversation. But when a physicist uses the word, it takes on a very different shape, one that quickly dissolves under closer inspection. Nothing in science isn't simply the absence of stuff, the way an empty box might appear to be. It becomes a concept tangled with space, energy, fields, and the very structure of reality itself. So, what do physicists mean when they try to describe nothing? At first glance, it sounds obvious. Nothing should mean the complete absence of anything at all. No matter, no energy, no space, no time, a void, a true blankness. But the problem begins the moment you try to define it rigorously, because physics is a science of what can be measured and observed, and if something is truly nothing, how would you measure it? How would you know it's there? Already we run into the first paradox. If nothing is really nothing, then perhaps it cannot be a part of science at all. Yet scientists keep returning to it, because in trying to describe what nothing is, they find themselves uncovering deeper truths about the universe. In the classical view, especially during the early centuries of natural philosophy, nothing was equated with a vacuum. Think of a sealed jar, all the air sucked out, leaving an empty space inside. To early thinkers, that seemed like the best approximation of nothing. But even that simple idea sparked fierce debate. Some argued that a vacuum couldn't exist, that nature abhors emptiness. Others claim that space could be emptied and still exist as an independent stage, a backdrop against which everything else unfolds. This tug-of-war between interpretations became the seed for later revolutions in science. Because if nothing can exist, then what exactly is the stage where something takes place? For many centuries, philosophers were at the front of this debate. Aristotle, for example, denied the possibility of true voids, insisting that every region of space must be filled with something, even if it was just air or some unseen substance. Later thinkers in the medieval and Renaissance periods wrestled with the same problem, building arguments for and against the void. What's interesting is that each time someone tried to pin down what nothing meant, they revealed more about how they viewed reality as a whole. A belief in voids suggested that space itself was real and could exist without matter. A denial of voids suggested that space was just a relation between objects. Centuries before modern physics, the seeds of the great debate had already been planted. Fast forward to the 17th century, and the issue of nothing took on a new clarity with Isaac Newton and René Descartes. Newton believed space was absolute, a container that existed independently of the matter within it. Even if you stripped away every star, planet, and particle, space itself would still be there, stretching endlessly. In this view, nothing was never truly nothing. At the very least, empty space would remain. Descartes, on the other hand, saw things differently. To him, space without matter wasn't really anything at all. Without things to fill it, there could be no meaningful concept of emptiness. These contrasting views foreshadowed the central puzzles physics would struggle with centuries later. But when modern physics arrived, the meaning of nothing grew even stranger. Consider the vacuum in Newton's time. To him, empty space was truly empty. It had no properties of its own, no energy, nothing to disturb or influence the things placed inside it. But as experiments advanced, it became clear that this wasn't quite true. Even a vacuum had measurable effects, and with the rise of quantum mechanics in the 20th century, that insight exploded into something far more radical. Physicists discovered that what we call empty space isn't truly empty at all. Instead, it's alive with fluctuations, teeming with activity that cannot be removed no matter how much you try. Nothing, in other words, is always something. This is where the distinction between everyday language and physics becomes sharpest. If you say your fridge has nothing in it, you mean there are no groceries. but the fridge still contains air molecules, stray photons of light bouncing off its interior walls, perhaps a bit of dust. From the standpoint of physics, that's not nothing at all. Even if you pumped all the air out of the fridge, what's left is still far from empty. There would still be electromagnetic fields, faint radiation from the environment, and most importantly, the quantum vacuum itself. When physicists talk about nothing, they are rarely speaking about absolute absence. Instead, they're referring to the state with the lowest possible energy, a condition called the vacuum state. And even that vacuum is restless. One way to appreciate this is through the uncertainty principle. Quantum mechanics tells us that certain pairs of physical quantities cannot both be zeroed out at the same time, position and momentum for instance, or energy and time. Because of this rule, even if you try to remove every last bit of energy from a region of space, tiny fluctuations remain. Virtual particles appear and disappear in fleeting moments, never existing long enough to be directly observed, but leaving behind subtle effects that can be measured. The Casimir effect is one famous example, where two metal plates placed very close together in a vacuum feel a tiny attractive force because of changes in the quantum fluctuations between them. Nothing, it turns out, has weight. This redefinition of nothing as a seething quantum vacuum reshapes the way physicists think about the universe. Suddenly, what we once thought of as an absence becomes a presence in disguise. Space is not a static backdrop, but an active player in the unfolding of events. In this sense, the idea of nothing leads to profound questions. If the vacuum is not truly empty, then what would it mean to imagine an absence of even space itself? Is that even a meaningful concept? Some physicists argue that without space and time, there is no framework in which physics can operate. Others suggest that new theories, such as quantum gravity, may eventually show us what it means to strip reality down further, to a level where even space emerges from something more fundamental. The language of nothing is therefore slippery. To a layperson, nothing might mean a bare room or an empty shelf. To a classical physicist, it might mean empty space with no matter in it. To a quantum physicist, it means a vacuum state, humming with fluctuations and energy that cannot be erased. And to those working on cosmology, nothing might even be the source of the universe itself, a state out of which space, time, and matter all emerged in a vast expansion. What becomes clear is that there is no single definition of nothing in physics. Each era, each theory reshapes the concept, showing us that emptiness is never quite as empty as it seems. It's worth pausing to reflect on just how radical this is. Imagine someone in the early 1800s being told that empty space was alive with invisible energy, producing fleeting particles that flicker in and out of existence. It would sound like pure fantasy. Yet, today, we have experiments confirming these effects, and technologies that rely on them. Vacuum fluctuations are real, measurable, and unavoidable. Nothing has structure, nothing has consequences, and nothing, quite literally, is the foundation on which everything rests. When we ask what physicists mean by nothing then, the answer is layered. At the surface, it means the absence of particles or fields we can detect directly. But just beneath that surface, it means a restless quantum vacuum. Deeper still, it may mean the absence of spacetime itself, a state that we do not yet fully understand, but which some theories of quantum gravity hint at. Each layer of nothingness reveals more complexity, more structure, and more puzzles. And far from being a simple absence, it becomes one of the most important concepts in physics, because it tells us what reality is made of at its most fundamental level. As you let this thought settle, notice how the idea of nothing has shifted. It's no longer a blank space on a page, but a kind of hidden canvas, alive with unseen brushstrokes. It's the ground state of existence, the starting point from which particles and forces arise. The very act of trying to remove everything reveals that something always remains. This realization doesn't just challenge our understanding of physics, it reshapes the way we think about existence itself. Because if nothing cannot exist, then perhaps the universe was inevitable. And if the vacuum is unstable, perhaps creation is built into the fabric of reality. When we move from the modern picture back into the age of Newton, the meaning of emptiness takes on a much sharper contrast. The world of the 17th century was caught in a transformation, shifting from centuries of philosophy and speculation toward the structured methods of modern science. At the centre of this change was a struggle over the very idea of the vacuum. Could space exist without matter, or was the notion itself nonsensical? To us today, with images of outer space filling our screens, the idea of emptiness might seem obvious, but in Newton's time, the existence of true empty space was far from settled, and the debate over it helped shape the foundations of classical physics. The story begins with an ancient inheritance. Aristotle had famously rejected the possibility of a vacuum. His reasoning was partly philosophical, but it also rested on what seemed like common sense. If you remove everything from a region of space, how could motion occur there? How could an object move into a void if there was nothing to displace or no medium to carry it along? For Aristotle, nature abhorred a vacuum, a phrase that would echo for centuries. Medieval scholars debated variations of this argument, some insisting that a void was impossible, others proposing ways it might exist under extraordinary conditions. But all of this was largely speculative, rooted in logic and language more than in experiment. By the early modern period, experiment began to push back against Aristotle's ban on emptiness. Engineers and natural philosophers working with pumps and barometers discovered they could create regions of space that seemed almost devoid of air. Evangelista Torricelli, in the mid-1600s, demonstrated that mercury could be used to trap a column of vacuum at the top of a tube, a discovery that both fascinated and unsettled his contemporaries. Blaise Pascal carried these experiments further, climbing mountains with barometers to show that air pressure decreases with altitude, evidence that air itself is a kind of weight pressing down on us, and that vacuums could indeed be created in limited form. Suddenly, the impossible was not only possible but measurable. Into this world stepped Isaac Newton. His Philosophia Naturalis Principia Mathematica, published in 1687, didn't just present a new system of mechanics, it redefined the way scientists thought about space itself. Newton treated space as absolute, a kind of infinite stage on which all physical events unfold. According to him, even if every star and planet were stripped away, this stage would remain. Space was not dependent on matter, it had an independent existence. That meant a vacuum, an empty region of space with no particles, was not only possible but natural within his framework. The void was simply space without things in it. This was a profound shift. To imagine space as something that exists on its own, independent of the bodies it contains, was to grant reality to emptiness. In Newton's universe, the vacuum wasn't a strange anomaly or a loophole in nature, but a central feature of how the cosmos was structured. His laws of motion assumed that objects could move freely in space, unimpeded by any medium. In fact, this was part of what made his system so powerful. Previous models often assumed that some kind of ether or substance had to fill all of space in order for planets to move or light to travel. Newton swept this aside. Motion could be explained with forces acting at a distance, and space itself could be empty. Yet, not everyone agreed. Newton's view of absolute space was challenged by other thinkers, most notably Gottfried Wilhelm Leibniz. To Leibniz, space without matter was meaningless. It was not a thing in itself, but a relation among objects. Remove the objects, and the concept of space vanishes too. This dispute between Newton and Leibniz wasn't just a technical detail. It was a philosophical clash over whether nothing could exist as something. Newton insisted that space was like a container, always present, always real, even if nothing occupied it. Leibniz countered that emptiness was a fiction, a kind of grammatical trick. This debate would echo far into the future, resurfacing in the 20th century when Einstein redefined space and time once again. But in the Newtonian world, the container view of space triumphed. It gave scientists a clear and practical framework. The vacuum became a legitimate concept, an actual condition in which experiments could be conducted, and experiments did follow. The air pump, refined by Robert Boyle, allowed researchers to study phenomena in evacuated chambers. They found that sound could not travel through a vacuum, confirming that air was necessary for its propagation. They observed flames sputtering and dying when deprived of air, and small animals struggling to survive in evacuated jars, gruesome but instructive demonstrations that life depended on the atmosphere. These experiments did not prove the existence of perfect nothingness, but they showed that regions emptied of ordinary matter behaved in striking ways. For Newton, the vacuum also solved practical problems in celestial mechanics. His law of universal gravitation described how every mass attracts every other mass across space. But if space were filled with some resisting medium, planets would be slowed in their orbits, their motions dampened over time. The very stability of the solar system, with planets circling the sun for eons, seemed to demand a near-perfect vacuum. The heavens were not thick with ethers or fluids, but vast, empty expanses where gravitational forces acted unobstructed. In this way, nothingness became an essential part of the architecture of Newton's cosmos. It's worth remembering how radical this was. To declare that the universe is filled mostly with emptiness went against centuries of intuition. On Earth, we are surrounded by tangible matter, by air, water, soil, and structures. Emptiness seems rare, almost unnatural. Newton turned this perspective on its head, suggesting that emptiness is actually the default and that matter is the exception. The stars and planets are scattered islands in an otherwise infinite sea of nothing. To the modern ear, this sounds familiar, but in the 1600s, it was revolutionary. Still, Newton's nothingness was not absolute in the way modern physics would later conceive it. His vacuum was truly empty of matter, but space itself remained as a fixed, unchanging backdrop. In other words, there was always something left, even when the matter was gone. That something was absolute space, immutable, unaffected by the presence or absence of material bodies. This assumption worked well for the mechanics of his time, but it carried with it certain mysteries. For example, how could gravitational forces act across empty space without a medium? Newton himself admitted he could not explain this, famously writing that he made no hypotheses about the cause of gravity. The action at a distance remained troubling, but his framework demanded it. The classical vacuum therefore held a dual role. On the one hand, it was emptiness, a region stripped of matter. On the other hand, it was still a structure, an arena that persisted whether or not anything occupied it. In Newton's world, nothing was never quite nothing. There was always the silent presence of space, the stage on which everything unfolded. This compromise allowed classical physics to flourish, providing a foundation for mechanics, astronomy, and early experiments with light and matter. But it also left unresolved questions, the kind that would come back with force when relativity and quantum theory entered the scene. One of the more fascinating aspects of this period is how quickly the vacuum moved from being a philosophical speculation to an experimental reality. Boyle's air pump and Torricelli's barometer didn't create perfect emptiness, but they produced conditions that were empty enough to challenge old assumptions. They showed that vacuums had properties, that the absence of air changed the behavior of sound, light, and fire. In a sense, these devices revealed that nothing was a state you could probe, test, and learn from. The vacuum became not just an idea, but a laboratory tool, a way to uncover the laws of nature. This was a turning point because it meant nothing could be studied empirically. From here, classical physics would extend the concept of vacuum into new territories. Experiments with light led to renewed debates about whether an invisible medium, the ether, filled space. For many scientists in the 18th and 19th centuries, the idea of a truly empty vacuum remained unsettling, and the ether served as a compromise. It was imagined as a subtle substance that filled all of space, allowing waves of light to propagate much like sound waves travel through air. For Newton, light was composed of particles, so the ether was unnecessary. But for wave theories of light, the ether seemed essential. The vacuum once again stood at the centre of controversy, forcing physicists to question whether nothing could really exist on a cosmic scale. Although the ether debate belongs more to the later centuries, it highlights how Newton's concept of vacuum was both liberating and incomplete. It freed physics from the Aristotelian rejection of emptiness, giving scientists permission to think of space as independent and real. But it also opened the door to new puzzles, because the vacuum was never truly nothing. It was either the container of absolute space, as Newton described, or it risked being filled with invisible substances to account for unexplained phenomena. The tension between emptiness and hidden presence would continue to drive inquiry for generations. When we look back on the classical vacuum now, it feels both familiar and distant. Familiar, because we still talk about outer space as a near-perfect vacuum, and we use Newton's mechanics in countless practical applications. Distant, because we know that Newton's absolute space has been replaced by Einstein's curved spacetime, and that the vacuum is far from empty in the quantum sense. But it's important to see how Newton's conception prepared the ground for these later revolutions. By making space independent and real, he gave physicists a framework in which to imagine emptiness as a legitimate state. By insisting that planets move through vast voids, he normalized the idea that most of the universe is nothing. And by framing the vacuum as an essential part of his mechanics, he set the stage for the deeper puzzles that would follow. The classical vacuum, then, is more than just a historical curiosity. It's a reminder that even the simplest concepts in physics carry layers of meaning. What seemed like empty space turned out to be a structured entity, essential for defining motion and forces. It solved some problems while creating others, and most importantly, it shows us how the idea of nothing has never been static. Each generation redefines it, testing it against the boundaries of knowledge and discovering that emptiness is never quite as empty as it first appears. When the 17th century ushered in a new era of scientific thought, the debate over nothingness became far more than a philosophical curiosity. It was woven into the heart of physics itself, shaping how people imagined the universe, how they explained motion, and how they thought about the invisible stage on which all of reality might unfold. Two of the most prominent voices in this debate were René Descartes and Isaac Newton. Their disagreement over the existence of the void wasn't just a quarrel about definitions. It was a clash between two radically different worldviews, each offering a foundation for science that would echo for centuries. To understand the argument, it helps to first step into Descartes' universe. Descartes believed that nature was fundamentally full. There could be no such thing as an empty space. For him, extension, the very property of taking up space, was identical to matter itself. In other words, the idea of space separate from substance was incoherent. If you imagined stripping away every particle, every speck of matter, you wouldn't be left with a void. You would be left with nothing at all, and that was the same as saying there was no space. In his system, matter and space were inseparable. This view had deep consequences. It meant that the universe was a continuous plenum, a great sea of substance without gaps. If objects moved, they did so not through empty space but by pushing against and displacing other parts of this continuous medium. Think of stirring a spoon through honey. Every motion is transmitted through the substance. For Descartes, this was how nature operated. Planets moved through great cosmic vortices of subtle matter. Motion was always relative, always part of this grand interconnected plenum. Newton's view couldn't have been more different. In his conception, space was absolute, a real thing in its own right. It was infinite, unchanging, and present regardless of whether any matter occupied it. Objects could move through this space freely. governed by forces acting at a distance. The universe wasn't a continuous honey-like medium. It was a vast empty stage, sparsely populated by bodies that interacted with one another according to precise mathematical laws. In Newton's system, the void was not only possible but necessary. Without it, his laws of motion and gravitation would make little sense. The clash between these perspectives was more than academic. It raised urgent questions about how motion itself should be understood. Descartes insisted that all motion must be relative. Without fixed empty space, there could be no absolute rest or absolute velocity. Newton countered that absolute space was real and measurable, even if indirectly. He devised thought experiments to prove his case, the most famous being the rotating bucket. Imagine a bucket filled with water suspended by a rope. Twist the rope and let it unwind, and the bucket begins to spin. At first the water remains still, its surface flat. Gradually, as the spinning continues, the water begins to rotate as well, its surface curving into a concave shape. For Newton, this showed that rotation was not merely relative to nearby objects. The curved surface revealed that the water was rotating with respect to absolute space itself. Without absolute space, he argued, this effect couldn't be explained. Descartes and his followers saw things differently. They argued that what mattered was the relation of bodies to one another. For them, absolute space was a meaningless abstraction, a mathematical fiction rather than a physical reality. If the water's surface curved, it was because of relative motion with respect to the surrounding plenum. There was no need to posit a mysterious container of absolute space. The dispute wasn't just about one bucket of water. It was about whether the universe was best described as a continuous medium or as a vast emptiness. This battle over the void spilled into broader scientific debates of the time. Descartes' insistence on a plenum supported his mechanical philosophy, where all natural phenomena were explained by contact interactions. Forces at a distance, such as Newton's gravity, seemed almost magical to him. How could one body influence another across empty space with nothing in between? For Descartes, that was unacceptable. Everything had to be explained by matter pushing or pulling against other matter in direct contact. Newton, by contrast, was willing to embrace action at a distance, even though he admitted he didn't know the underlying cause of gravity. What mattered to him was that the mathematics worked and matched observation. This willingness to let the void exist gave Newton's physics extraordinary predictive power. His laws of motion and universal gravitation could explain falling apples, the paths of cannonballs, and the orbits of planets with one consistent framework. By contrast, Descartes' vortices of subtle matter were elegant in theory, but fell short in precision. They couldn't account for the detailed motion of celestial bodies. Observations gradually favoured Newton's system, and with it, the idea that empty space was real and fundamental. Still, the Cartesian challenge never disappeared completely. The unease with Newton's action at a distance lingered among many of his contemporaries. Even Newton himself admitted he made no hypothesis about the mechanism of gravity. He didn't claim to know how bodies attracted one another across empty space. He only described that they did. This humility left room for later theories to build upon his work. But it also underscored the radical nature of his conception of space. He had elevated nothing into a real, physical backdrop against which the drama of the cosmos unfolded. One way to appreciate the depth of this disagreement is to see how each thinker's view connected to their broader philosophy. Descartes believed in a tightly ordered universe governed by clear mechanical rules. A plenum universe fit his desire for rational clarity. It avoided mysterious voids or forces that could not be reduced to contact interactions. Newton, though equally committed to rational science, was willing to accept a universe with hidden depths, where forces might operate invisibly and where space itself had an independent existence. Their dispute was not only scientific but metaphysical, touching on what it means for something to exist at all. In the centuries that followed, the Newtonian view became dominant, largely because it was more successful at explaining and predicting the natural world. The void became an accepted part of the scientific imagination. Telescopes revealed vast empty distances between the stars, reinforcing the image of a universe filled mostly with nothing. Experiments with vacuums on Earth provided tangible demonstrations of emptiness. The Cartesian plenum gradually receded, remembered more as a stepping stone than as a lasting framework. Yet, when we look back with modern eyes, the debate appears less settled than it once seemed. For all of Newton's success, his absolute space was eventually challenged by Einstein's relativity. In Einstein's framework, space and time are not rigid containers, but dynamic entities shaped by matter and energy. In a strange way, this echoes some of Descartes' skepticism. The idea that space could exist entirely independent of matter has become more complicated, and the notion of a continuous fabric underlying everything, though very different in form, is not so far from the old Cartesian plenum. History doesn't repeat itself exactly, but it rhymes in curious ways. This makes the battle between Descartes and Newton more than a historical footnote. It was an early glimpse of the tension that continues to run through physics, the struggle to decide whether emptiness is real or whether it's always filled by something deeper, something invisible. Every time science pushes the boundaries of knowledge, it seems to circle back to the same question. Can there ever be nothing? Or is nothing always a disguise for something we haven't yet recognized? Seen from this perspective, the 17th century clash was the first great confrontation over the void, a confrontation that set the stage for everything that followed. Newton may have won the immediate battle, securing a place for absolute space and vacuum in classical physics, but Descartes' concerns, his refusal to accept action across emptiness, his insistence that space and matter are inseparable, continue to echo in modern debates about quantum fields, spacetime, and the ultimate fabric of reality. When the 20th century began, the void of Newton's universe seemed secure. For more than 2 centuries, scientists had treated space as a rigid stage, fixed and absolute, independent of the matter that danced across it. Telescopes had mapped the heavens against this backdrop, and mechanics had explained motion with astonishing precision. Nothing, in Newton's sense, was simple. It was the empty expanse that held everything together. But as new questions emerged, and as experiments began to probe the limits of classical mechanics, cracks appeared in this picture. At the centre of this shift stood Albert Einstein, whose theories of relativity would forever change the way physicists thought about space, time, and the very nature of nothing. To grasp the depth of this change, it helps to see what relativity was reacting against. Newton's laws had worked extraordinarily well for centuries. They described falling objects, planetary orbits, and even the motion of comets with uncanny accuracy. But there were hints that something deeper was waiting to be uncovered. Light, for example, stubbornly resisted attempts to fit it neatly into Newton's framework. Experiments showed that its speed was always the same, regardless of how fast the source or the observer was moving. This didn't make sense in a universe with absolute space and time. If motion was relative, shouldn't the speed of light also shift depending on your frame of reference? Yet no experiment ever showed such variation. At first, scientists tried to resolve this puzzle by adding another unseen medium. They called it the luminiferous ether, a subtle substance thought to fill all of space, carrying light waves the way air carries sound. It was a modern echo of the old Cartesian plenum, an attempt to deny the possibility of true emptiness. But the ether proved elusive. Experiments designed to detect Earth's motion through this cosmic medium consistently came up empty. The famous Michelson-Morley experiment of 1887 delivered the most decisive blow, failing to find any trace of ether winds as the Earth moved around the Sun. It was as if light needed no medium at all, as if space itself carried its waves. Einstein's special theory of relativity, published in 1905, swept aside the ether, and with it the last comfort of Newton's absolute stage. He proposed that the laws of physics are the same in all inertial frames of reference, and that the speed of light is constant for all observers. These two postulates had astonishing consequences. They meant that space and time could no longer be separate, fixed quantities. Instead, they merged into a single four-dimensional fabric called spacetime, where distances and durations depended on the state of motion of the observer. What one person called a second might be longer or shorter for another, depending on their speed. What one called simultaneous, another might call sequential. This alone was enough to shatter the old conception of nothing. No longer could space be thought of as a neutral, unchanging container. It was part of a dynamic fabric woven together with time itself. The emptiness between objects was not absolute. It shifted depending on how you moved through it. Nothing had become relative. A decade later, Einstein expanded his vision into the general theory of relativity, and here the transformation became even more profound. In Newton's world, gravity was a force acting at a distance across empty space. The sun pulled on the earth pulled on the moon, and all of it unfolded against the silent background of absolute space. In Einstein's world, gravity was not a force at all. It was the curvature of space-time itself. Matter told space-time how to bend, and space-time told matter how to move. Suddenly the void was no longer passive. It was dynamic, malleable, and active in shaping the behavior of the cosmos. This was a radical break with centuries of thinking. For Descartes, emptiness had been impossible because space and matter were inseparable. For Newton, emptiness had been real, a fixed stage that existed independently of matter. For Einstein, emptiness became a participant, a flexible fabric that responded to the presence of mass and energy. Nothing, in this sense, could curve. It could stretch, compress, and ripple. It could guide the motion of planets and bend the paths of light. Emptiness itself had become a physical entity. One of the most striking confirmations of this view came in 1919, during a total solar eclipse. Einstein's theory predicted that light passing near a massive body like the Sun would be bent by the curvature of space-time. During the eclipse, astronomers measured the positions of stars near the darkened Sun and found them displaced exactly as relativity predicted. Empty space near the Sun was not empty at all. It was warped by the Sun's gravity, and that curvature altered the path of light itself. Nothing, it seemed, had power. Over the following decades, more evidence piled up. The orbit of Mercury, long known to deviate slightly from Newtonian predictions, was explained perfectly by general relativity. Time itself was shown to run differently depending on gravitational potential. Clocks placed at different heights in Earth's gravity ticked at slightly different rates, just as Einstein had predicted. Emptiness, once thought to be neutral and unchanging, had become a landscape of valleys and hills, shaping time and motion alike. Perhaps the most dramatic consequence of this reimagining was the prediction of black holes. If enough mass were concentrated in a small region, the curvature of space-time could become so extreme that not even light could escape. The result was not merely a dark object, but a region of space-time where the very notion of empty space breaks down. Inside such an object, the geometry of nothing collapses into a singularity, a point where the fabric of space-time itself ceases to be describable by current physics. Here, the question of whether nothing can curve takes on a sharper edge. At the heart of a black hole, it is not clear whether we can speak of space, time, or nothing at all. Another extraordinary consequence was the realization that space-time itself could expand. In Newton's universe, space was infinite and unchanging, a fixed backdrop against which matter moved. In Einstein's framework, the equations allowed for a dynamic cosmos. Solutions to his field equations revealed universes that could expand or contract, where the very emptiness between galaxies could stretch over time. Initially, Einstein resisted this, introducing the cosmological constant to hold the universe static. But later discoveries, especially Edwin Hubble's observation of galaxies moving away from us, confirm that the universe is indeed expanding. Nothing is not fixed, it evolves, carrying galaxies apart as space-time itself stretches. This realization reshaped cosmology. It meant the universe had a history. If it is expanding now, then in the past it must have been denser and hotter. Follow that reasoning far enough, and you reach a moment when all of space and time were compressed into an initial state. The Big Bang was not an explosion into empty space. It was the creation of space and time themselves. Nothing in the Newtonian sense never existed at all. There was no void waiting for the universe to fill it. The fabric of space-time came into being with the cosmos. Emptiness was born alongside matter and energy, inseparable from them. This reframing of nothing has profound implications. It means that when we ask whether the universe could come from nothing, we must first decide what kind of nothing we mean. The nothing of Newton, the empty container waiting to be filled, was an illusion. In Einstein's framework, emptiness itself is something, a structure that bends, curves, and evolves. And if space-time has physical properties, then the true absence of anything, even of space and time, lies outside our current understanding. Einstein brought us closer to that edge, but he also showed us that what we once called nothing is far richer and more dynamic than anyone imagined. As experiments grew more precise, the fingerprints of curved space-time appeared everywhere. Gravitational lensing, where massive galaxies bend the light of objects behind them, revealed the fabric of emptiness acting like a cosmic lens. Time dilation near strong gravitational fields showed that clocks in orbit around Earth ticked faster than those on the surface, forcing engineers to correct for these effects in GPS satellites. Even ripples in space-time itself, gravitational waves, were predicted by Einstein's equations and finally detected a century later, as enormous observatories measured faint oscillations in emptiness, caused by colliding black holes billions of light-years away. Nothing, far from being powerless, carried the echoes of some of the most violent events in the cosmos. Through all of this, the meaning of nothing in physics shifted dramatically. What Newton had treated as absolute emptiness became a living, dynamic entity. Space was no longer neutral, no longer untouchable. It was elastic, sculpted by matter, and in turn sculpting the motion of matter. This new view didn't just add detail to the old one, it overturned it completely. Nothing could curve, and that simple idea changed our understanding of the universe forever. Yet, Einstein's revolution also opened the door to new mysteries. If space-time itself is dynamic, then what lies beneath it? Is it truly fundamental, or will it eventually give way to something deeper, something more like the old plenum than the rigid stage? Modern physics, particularly in the realms of quantum theory and attempts at quantum gravity, continues to wrestle with these questions. The story of nothing did not end with relativity. It only became more entangled as quantum mechanics began to reveal that even the vacuum is restless, filled with fluctuations and energy that never disappear. And so the journey from Newton to Einstein is not just a shift in mathematics, it is a shift in imagination. It shows us that the simplest concept, the idea of emptiness, is anything but simple. What we once thought of as nothing turns out to be curved, elastic, and alive with structure. And as the 20th century moved forward, physicists would discover that this was only the beginning. Nothing in the quantum world would become stranger still. By the time Einstein had reshaped our understanding of space and time, physicists already suspected that the story of nothing was not finished. Relativity had shown that emptiness could curve, stretch, and ripple, that the stage of the universe was alive in ways Newton never imagined. But another revolution was brewing, one that would strike even deeper at the meaning of emptiness. Quantum mechanics, developed in the early decades of the 20th century, revealed that nothing is not only structured but restless, filled with a subtle energy that never goes away. What seemed like empty space became a buzzing sea of activity. The vacuum, once a synonym for absence, was now one of the most complex and important concepts in modern physics. To appreciate this transformation, it helps to start with the uncertainty principle. Werner Heisenberg's insight, published in 1927, stated that there are fundamental limits to how precisely we can know certain pairs of physical quantities. Position and momentum form one famous pair, energy and time form another. This second version is crucial for the vacuum. It means that over very short intervals, energy does not need to be perfectly conserved. Instead, small fluctuations can occur, borrowing energy briefly before returning it just as quickly. In most contexts, these fluctuations are tiny, but in the context of nothing, they make all the difference. Imagine stripping away all particles, all radiation, and all fields from a region of space. You might think you're left with perfect nothing, but quantum theory says no. Because of the uncertainty principle, energy can never be perfectly zero. Instead, the vacuum is filled with fleeting disturbances, momentary appearances of particle-antiparticle pairs that come into being and vanish again in unimaginably short timescales. These virtual particles cannot be directly observed, but their effects are measurable. In this sense, the vacuum is not nothing at all. It is the lowest energy state of a quantum field, but even at this minimum, it never stops fluctuating. One of the most famous demonstrations of these fluctuations is the Casimir effect, predicted in 1948 by Hendrik Casimir. He calculated that two uncharged metal plates placed very close together in a vacuum would experience a tiny attractive force, not because of any obvious interaction, but because the vacuum between them allows fewer modes of quantum fluctuation than the space outside. The imbalance creates a pressure that pushes the plates together. Later experiments confirm this prediction with remarkable precision. Nothing, it turns out, exerts a force what looks like empty space can push. Another striking consequence is the Lamb shift, a subtle change in the energy levels of electrons in a hydrogen atom. This effect, measured in the late 1940s, also arises from the interaction between electrons and the sea of vacuum fluctuations. The shifts are tiny, but they confirm that the vacuum influences matter at the quantum level. These discoveries forced physicists to accept that nothing is far from empty. The vacuum has structure, energy, and measurable consequences. The mathematics that emerged to describe this new picture is known as quantum field theory. In this framework, every kind of particle is associated with a field spread throughout space. Electrons, quarks, photons, all of them arise as excitations of underlying fields. The vacuum is the state of these fields when they are not excited, when they are as quiet as possible. But quiet in quantum mechanics is never absolute silence. Even at their lowest energy, fields fluctuate. And those fluctuations mean that the vacuum is a churning sea, a background that cannot be eliminated. This sea has profound implications for cosmology. When physicists calculate the energy associated with vacuum fluctuations, the result is enormous. In fact, the theoretical value is so large that if it were correct, the universe would have torn itself apart almost instantly. Observations show that the actual vacuum energy is much smaller, but not zero. The mismatch between the calculated value and the observed one is one of the greatest puzzles in modern physics, sometimes called the cosmological constant problem or the vacuum catastrophe. It suggests that our understanding of nothing is still incomplete, that there are hidden principles shaping the vacuum we have not yet discovered. The role of the vacuum in the expanding universe adds even more intrigue. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. The best explanation is that empty space itself carries an energy density, often called dark energy, that drives this acceleration. In other words, nothing is pushing the universe apart. The very fabric of spacetime, through its vacuum energy, is shaping the destiny of the cosmos. Once again, nothing proves to be one of the most powerful somethings. In particle physics, the vacuum plays another role tied to the Higgs field. The discovery of the Higgs boson in 2012 confirmed that particles acquire mass through interactions with a field that pervades all of space. The vacuum expectation value of the Higgs field is not zero. This non-zero value is why particles like electrons and quarks have mass at all. Without it, the universe would be radically different, with no atoms, no chemistry, and no life. The fact that the vacuum is structured in this way shows that emptiness is not neutral. It is configured with properties that determine the very possibility of matter as we know it. This raises deep philosophical questions alongside scientific ones. If the vacuum is full of fluctuations, if it carries energy, if it shapes the motion of galaxies and gives particles their mass, can we truly call it nothing? Some physicists argue that the word is misleading, that what we call vacuum is better thought of as a medium with its own properties. Others point out that compared to the rich structures of matter and radiation, the vacuum is still a kind of nothing, the closest the universe ever gets to true emptiness. Either way, the word reveals its slipperiness. Nothing is never quite what it seems. The quantum vacuum also suggests ways the universe might have begun. Some cosmological models propose that fluctuations in the vacuum could spark inflation, a period of exponential expansion in the earliest moments of the universe. In this view, the seeds of galaxies, stars, and planets were sown by fluctuations in nothingness. What we see today, the grand architecture of the cosmos, may trace its origins to the restless activity of the vacuum itself. The same principle that creates tiny shifts in atomic energy levels may have sculpted the entire large-scale structure of the universe. These insights do not close the book on nothing. Instead, they open new chapters filled with unresolved puzzles. The vacuum energy problem, the nature of dark energy, the relationship between quantum fields and space-time itself, all of these remain unsettled. Each time physics has tried to define nothing more precisely, it has uncovered new layers of complexity. What once seemed like absence becomes presence. What once seemed silent becomes active. The more carefully we study the vacuum, the more it appears to be the foundation of reality, the background from which everything else emerges. This shifting view also connects back to the old debates of Descartes and Newton. In a strange way, quantum field theory echoes Descartes' suspicion that emptiness is never truly empty, that some medium must pervade space. But it also keeps Newton's insight that space itself can exist independently of matter. The quantum vacuum is both stage and substance, both absence and presence. It shows how the questions raised centuries ago continue to evolve, reshaped but never fully resolved. What makes this especially striking is that the vacuum is not only a theoretical construct. Its effects are measured, quantified, and used in practical technologies. Precision atomic clocks account for vacuum-induced shifts. Quantum electrodynamics, the theory that incorporates vacuum fluctuations, produces predictions that match experiments to astonishing precision, sometimes better than 1 part in a trillion. Nothing studied with enough care yields results that rank among the most accurate in all of science. And yet, the paradox remains. If the vacuum is filled with energy, why does it not dominate the universe? If virtual particles appear and vanish constantly, what is the true nature of their existence? Are they real, or are they only a mathematical device to describe the behavior of fields? Physicists debate these questions vigorously because the answers touch on the very foundations of reality. Nothing, in the quantum sense, resists simple interpretation. The exploration of the vacuum is not finished. As new experiments push the limits of precision, and as theories of quantum gravity attempt to merge quantum mechanics with relativity, the meaning of nothing may shift again. Perhaps space-time itself will turn out to be emergent, a construct built from something deeper. If that is true, then what we now call the quantum vacuum may itself be only an approximation, a surface glimpse of a more fundamental structure. Nothing may still have secrets to reveal. As the 20th century gave way to the 21st, physicists found themselves returning to the same question that puzzled ancient philosophers. Can nothing exist? The answer, in quantum physics, seems to be both yes and no. Yes, in the sense that regions can be emptied of particles and radiation. No, in the sense that the vacuum always remains, always fluctuates, always carries energy. What we call nothing is always something, and perhaps that is the deepest lesson of all. The restless vacuum, alive with fluctuations, becomes the bridge to even stranger questions. If quantum fields ensure that nothing is never truly empty, then what happens when we look deeper still, at the possibility that space-time itself may not be fundamental? What if nothingness is only an emergent appearance, a shadow of more hidden dynamics? When the language of quantum theory introduced the idea of fluctuations in the vacuum, it also brought with it a peculiar concept that seems almost paradoxical. Physicists began to speak about particles that appear and disappear in a heartbeat, not as permanent residents of reality, but as temporary disturbances. They were given the name virtual particles. The phrase has become popular far beyond the walls of physics, often described in books, articles, and even casual conversations as something coming out of nothing. But to understand what these entities truly mean, and what they don't, requires careful attention, because they do not behave like ordinary particles, and yet they leave measurable fingerprints on the world. In classical physics, particles are straightforward objects. A grain of sand, a drop of water, a planet orbiting a star. Each one has a definite position, a definite motion, and a clear existence in space and time. Quantum mechanics changes that picture. Here, the state of a particle is described by probabilities, by waves of possibility rather than fixed certainty. When you add quantum field theory into the mix, particles are no longer independent objects at all. They are excitations of fields, ripples in a deeper background that spans the universe. Within this framework, the vacuum is the ground state of the fields. But even in that ground state, disturbances arise. The mathematics of the theory treats these disturbances as if they involve particles briefly existing, only to vanish again almost immediately. Virtual particles are not real in the same sense as electrons, photons, or protons. They cannot be directly detected. They cannot be put into a detector and recorded as discrete events. Instead, they exist as part of the internal machinery of quantum interactions. When physicists calculate the probability of one particle scattering off another, they represent the possible paths through diagrams, often called Feynman diagrams after the physicist Richard Feynman who popularized them. In these diagrams, real particles enter and leave, while internal lines represent the exchange of virtual particles. These virtual entities are mathematical contributions to the calculation, but the fact that they are not directly observable does not mean they are irrelevant. The predictions that emerge from these calculations match experimental results with extraordinary accuracy. The behavior of atoms, the forces between particles, the interactions that build matter, all of them depend on the effects of virtual particles. A familiar example is the electromagnetic force. When two electrons repel each other, the simplest way to picture it in quantum field theory is to imagine them exchanging virtual photons. The photons are not real in the sense of being measurable light. They are temporary disturbances in the electromagnetic field, appearing only in the calculation, but their effect is real and measurable in the form of the repulsion we observe. In this way, virtual particles provide a way to describe how forces act at the quantum level. Another place they show up is in the vacuum fluctuations themselves. When we say the vacuum is teeming with activity, what we mean is that pairs of virtual particles and antiparticles momentarily come into being and then annihilate one another. These processes cannot be directly captured, but they influence the energy levels of atoms, the forces between plates in the Casimir effect, and even the behavior of fields on cosmological scales. Something comes out of nothing, but only for the briefest of times and only within the constraints of quantum uncertainty. This leads to a question that often arises in popular explanations. Are virtual particles really there, or are they just a mathematical trick? Physicists debate the best way to answer this. On one hand, they cannot be directly observed, so calling them real in the everyday sense can be misleading. On the other hand, their effects are measurable and essential to the consistency of quantum theory. Many prefer to say that they are a convenient language for describing interactions, a way to visualize what the mathematics is doing. What matters is that the predictions built on this concept agree with experiments to astonishing precision. In this sense, whether virtual particles are real is less important than the fact that they work. It is tempting to imagine virtual particles as little blips popping into existence in empty space, buzzing around for a moment, then vanishing again. This picture is vivid, and it is often used in outreach and education, but strictly speaking, the truth is more subtle. Virtual particles are not particles in the ordinary sense. They do not have to obey the same energy-momentum relations that real particles do. They are better understood as disturbances in the underlying fields that contribute to the overall behavior of interactions. In that sense, the term particle is a metaphor, a way of capturing a mathematical contribution in a more intuitive language. Despite this subtlety, the consequences of virtual particles are everywhere. In quantum electrodynamics, the most precise theory of how light and matter interact, virtual particles play a central role. They contribute corrections to the magnetic moment of the electron, corrections that have been measured in experiments to more than 10 decimal places. The agreement between theory and experiment here is one of the triumphs of modern science, showing that even though virtual particles cannot be directly seen, their influence is as real as any other effect in physics. In nuclear physics, the exchange of virtual particles is equally essential. The strong force, which binds protons and neutrons inside atomic nuclei, is described in terms of the exchange of virtual gluons. Without these exchanges, nuclei would not hold together and atoms would not exist. The stability of matter itself depends on the restless traffic of particles that are never directly observed. It is a reminder that what we call nothing, the space between, is not empty. It is filled with the potential for these interactions, constantly shaping the world. Even in cosmology, virtual particles play a role. During the early moments of the universe, quantum fluctuations amplified by inflation may have given rise to the tiny irregularities that later grew into galaxies and clusters of galaxies. In this way, the vast structures of the cosmos may trace their origin to virtual particles, fleeting disturbances in a primordial vacuum. What could be more striking than the idea that everything we see around us, stars, planets, people, owes its existence to the restless flickering of something that emerges from nothing? The phenomenon of Hawking radiation offers another dramatic example. In the 1970s, Stephen Hawking proposed that black holes are not entirely black. Instead, quantum fluctuations near the event horizon can produce pairs of virtual particles. Normally, these pairs annihilate quickly, but if one member of the pair falls into the black hole while the other escapes, the escaping particle becomes real, radiating away from the black hole. To an outside observer, it looks as though the black hole is emitting particles. Over time, this process can cause the black hole to lose mass and eventually evaporate. Once again, the physics of virtual particles turns the concept of nothing into a source of something, even in the most extreme environments in the universe. All of this raises deeper questions about the nature of reality. If virtual particles are indispensable to our best theories, if they shape forces and influence the cosmos, then what does that say about the boundary between existence and non-existence? The term virtual might suggest that they are not real, but their measurable effects suggest otherwise. In some ways, they blur the line between being and not being, showing that the categories we normally use may not apply at the quantum level. This blurring is what makes the idea so unsettling and so fascinating. It reminds us that our intuitive notions of something and nothing, of presence and absence, are not adequate when we peer into the quantum world. The vacuum is never truly empty. Disturbances that we call virtual particles constantly shape its behavior. And though they flicker out of existence almost as soon as they appear, The sum of their effects builds the stability of atoms, the interactions of forces, and perhaps even the structure of the cosmos itself. In the laboratory, efforts continue to probe these effects more directly. Experiments with high-intensity lasers, for example, aim to test whether the vacuum itself can act like a nonlinear medium, producing observable phenomena when exposed to extreme fields. These efforts are attempts to catch glimpses of the restless sea of virtual activity, not by detecting the particles themselves, but by observing the changes they induce in measurable quantities. Each such experiment is another step in turning the idea of nothing into a precise scientific concept. So when physicists say that something comes out of nothing, they do not mean that real particles simply pop into existence out of a void in the everyday sense. They mean that the quantum vacuum, with its fluctuations and disturbances, constantly produces effects that can be described as the temporary appearance of virtual particles. These appearances are part of the mathematics of how fields interact, and they have consequences that reach from the subatomic scale to the cosmic scale. Nothing in this view is never truly nothing. It is a dynamic stage where the lines between real and virtual, between presence and absence, are constantly crossed. The story of virtual particles is therefore not a side note, but a central part of how modern physics understands the universe. It shows that when we look closely, the vacuum is as rich and active as any other aspect of reality. It reveals that the forces holding the world together depend on things that exist only for an instant, things that we cannot observe directly, but without which nothing would function as it does. And it points forward, toward deeper questions about the nature of the vacuum, the origins of the universe, and the ultimate meaning of nothingness in physics. When physicists first uncovered the restless nature of the vacuum, they realized that something remarkable followed from the principles of quantum mechanics. Even when a system is cooled to its lowest possible temperature, even when every particle has given up as much energy as it can, there remains a residue, an irreducible minimum. This leftover energy is called zero-point energy. It is not something that can be drained away. It cannot be removed by cooling, or by shielding, or by any technique known to science. It is built into the very structure of quantum theory, the unavoidable hum of existence that never switches off. The idea is easiest to see when we look at the simplest quantum system, a particle trapped in a box or a spring-like oscillator. In classical mechanics, if you have a ball on a spring and you damp out its motion, you can in principle bring it to complete rest at the bottom. With no kinetic energy and no potential energy, the ball simply sits there, perfectly still. But quantum mechanics refuses to allow this. Because of the uncertainty principle, the position and momentum of the particle cannot both be precisely defined at the same time. If the particle were exactly at rest at the bottom, with zero motion and exact position, the uncertainty principle would be violated. Instead, the particle must always retain some residual motion, some jitter that never goes away. That motion corresponds to a non-zero amount of energy, the zero-point energy. Extend this logic from one particle to fields, and the conclusion becomes even more dramatic. Every quantum field, the electromagnetic field, the electron field, the quark fields and so on, possesses a ground state, and in each ground state there is zero-point energy. When you add up these contributions, the vacuum itself becomes a vast reservoir of energy. The irony is that this energy is invisible in daily life. It does not behave like a fuel we can tap or a heat we can feel, but it is there, unavoidable, shaping the world in ways that are subtle and sometimes profound. One of the most direct consequences is the Casimir effect, which we already touched upon earlier. The force between two plates in a vacuum is one manifestation of zero-point energy. The plates restrict the possible modes of fluctuation between them, leading to an imbalance compared to the outside, and this imbalance produces a measurable force. The fact that this can be detected experimentally shows that zero-point energy is not just a theoretical trick. It has tangible effects. It is woven into the behaviour of the vacuum itself. The Lamb shift in hydrogen atoms is another piece of evidence. the small correction in the energy levels of electrons arises because of interactions with the fluctuating electromagnetic field of the vacuum. Without zero-point energy, those fluctuations would not exist, and the predicted spectrum of hydrogen would be different. The measured spectrum matches the predictions that include zero-point contributions, confirming that this irreducible energy is real. At first, the existence of zero-point energy seemed almost an annoyance, a mathematical artifact of quantum theory. But as time passed, physicists began to realize its significance. In the 1910s, Albert Einstein and Otto Stern used the idea to explain residual motion in gases at very low temperatures. Later, it became central to quantum field theory, providing the foundation for understanding fluctuations and interactions. What began as an oddity turned into a cornerstone of modern physics. The scale of zero-point energy is mind-boggling. When theorists attempt to calculate the total vacuum energy by summing over all the possible fluctuations of all fields, the result is immense. The predicted density is so large that, if it were correct, the universe would not resemble the one we see. Space would be curved beyond recognition. The expansion rate of the cosmos would be catastrophic. The mismatch between theory and observation is sometimes described as the worst prediction in physics. Calculations overshoot the observed value by 120 orders of magnitude. This is the cosmological constant problem, the vacuum catastrophe. It shows that while zero-point energy is undeniably real, our understanding of its contribution on cosmic scales is still incomplete. Despite this mismatch, evidence suggests that vacuum energy does play a role in cosmology. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. The best explanation is that empty space itself carries a small, but non-zero energy density, often identified with dark energy. If that interpretation is correct, then zero-point energy is not just a laboratory curiosity. It is a cosmic driver, responsible for the accelerated expansion of the universe. Nothing, through its irreducible hum, is shaping the fate of everything. This picture has fueled speculation about whether zero-point energy could be harnessed. Popular culture sometimes imagines tapping the vacuum as an unlimited power source, a reservoir that could provide endless energy. But in practice, the situation is far more subtle. While zero-point energy exists, extracting useful work from it is not possible with any known process. The fluctuations are everywhere and uniform, leaving no gradient to exploit. Any attempt to draw from them would violate the basic principles of thermodynamics. Physicists remain skeptical that zero-point energy can ever be used as a technology in the way it is sometimes portrayed. Its significance lies not in what we can use it for, but in what it reveals about the structure of reality. One of the fascinating aspects of zero-point energy is its connection to temperature. When a system is cooled toward absolute zero, classical intuition says all motion should stop, but quantum mechanics insists otherwise. Even at absolute zero, particles continue to vibrate slightly, fields continue to fluctuate, and energy remains. This is why helium, for instance, never solidifies under normal pressure, no matter how much it is cooled. Its zero-point energy keeps its atoms moving enough to resist freezing. This everyday consequence shows how quantum rules, normally hidden, spill into the macroscopic world. The discovery of superconductivity and superfluidity also ties back to zero-point energy. These phenomena occur when quantum effects, normally confined to microscopic scales, manifest collectively in large systems. The persistence of current in a superconductor, or the frictionless flow of a superfluid, reflects the same principle, that even the lowest energy state is not silent. Quantum mechanics leaves traces that no amount of cooling or damping can erase. Zero-point energy also shapes the behavior of chemical bonds. The vibrational ground states of molecules are lifted above the classical minimum by this irreducible energy. Spectroscopy, the study of how matter interacts with light, must account for these shifts. Without them, the predictions would be off, and the match with experimental results would break down. Once again, the invisible residue of the vacuum asserts itself, guiding the behaviour of the physical world. As physics pushes toward unification, the role of zero-point energy becomes even more critical. In quantum gravity, for instance, the question arises, what happens to zero-point fluctuations when space-time itself is quantized? Do they persist? Do they take on a different form? These are open questions, ones that cut to the heart of the unfinished project of merging relativity and quantum mechanics. It may be that the vacuum, with its irreducible hum, holds clues to the ultimate nature of space-time. The notion that energy remains even when everything else is stripped away also connects to questions about the origin of the universe. Some cosmological models propose that fluctuations in a vacuum could trigger the birth of space and time themselves. If zero-point energy is unavoidable, then perhaps creation itself is an inevitable consequence of the laws of physics. The universe may have emerged not from pure nothing, but from the restless fluctuations that can never vanish. Of course, this interpretation depends on how one defines nothing. From the perspective of quantum field theory, the vacuum is already something, a structured state with properties. Calling it nothing is misleading, though it may be the closest physics comes to describing absence. The fact that this supposed absence has energy only reinforces the paradox. Nothing is never nothing. It is always charged with potential, always restless, always humming with zero-point activity. What makes this particularly striking is that zero-point energy is not an exotic side effect visible only in extreme conditions. It pervades everything, everywhere. It is as much a part of the vacuum in your living room as it is in the depths of intergalactic space. You don't notice it because it is uniform and ever-present, but it is there all the same. The realization that even the most familiar emptiness is alive with unavoidable energy changes how we think about reality. It tells us that nothingness is not silent or inert, but foundational and dynamic. The recognition of zero-point energy was a turning point in physics, one that continues to reverberate. It showed that the vacuum is not a neutral background, but an active player. It revealed that energy persists even in the absence of particles and fields, and it hinted at mysteries that remain unresolved, from the cosmological constant problem to the nature of dark energy to the quest for quantum gravity. Each of these puzzles grows from the simple fact that energy never vanishes completely. When physicists first began to suspect that the vacuum was not truly empty, they needed a way to test this bold idea. It was one thing to claim that fluctuations of energy existed invisibly in the background of space, but another to find a tangible effect, a way to measure the consequences of this unseen activity. The Casimir effect became one of the clearest demonstrations that the vacuum is not a void in the classical sense. Instead, it is a restless medium that can exert pressure, pull objects together, and show its presence even when everything else has been stripped away. It is one of those phenomena that seems almost magical when first described, but which follows inevitably from the principles of quantum field theory. The effect is named after the Dutch physicist Hendrik Casimir, who in 1948 was studying the behaviour of quantum fields confined between conducting surfaces. He considered two uncharged metal plates, placed parallel to one another, very close together, in a vacuum. Classically, nothing special should happen. With no charges, no currents, and no matter between them, the plates should simply sit there, unaffected. But when Casimir applied the rules of quantum theory, a surprising conclusion emerged. In a vacuum, the electromagnetic field is never completely still. Even in its lowest energy state, it fluctuates. These fluctuations can be described as virtual photons, appearing and disappearing constantly. Normally, these fluctuations span a wide range of wavelengths, filling all of space. But when two conducting plates are placed close together, the situation changes. The plates impose boundary conditions, meaning only certain wavelengths can fit neatly between them, while others are excluded. Outside the plates, by contrast, all wavelengths are allowed. This creates a tiny imbalance in the vacuum fluctuations. The energy density outside is slightly greater than inside. The result is a pressure that pushes the plates toward each other. The force is extraordinarily small, but it is real. Casimir predicted that as the distance between the plates shrinks, the effect grows stronger, though it remains so weak that only sensitive experiments could detect it. For decades, the Casimir effect was treated as an elegant but mostly theoretical curiosity. Measuring it directly was beyond the reach of experimental precision, but as technology advanced, especially with the development of sensitive instruments and techniques in the late 20th century, physicists began to confirm the effect. Today, experiments have measured the Casimir force to remarkable accuracy, showing that Casimir's prediction was correct. The vacuum does push back. The implications are profound. If empty space can exert a measurable force on physical objects, then empty space is not empty. It carries energy. It interacts. It has structure. This realization reshapes the way physicists think about nothing. The vacuum is not simply a backdrop against which matter moves. It is an active participant in the dynamics of the universe. The Casimir effect is not merely a detail of quantum electrodynamics. It is a window into the nature of reality itself. To understand why the effect is so significant, imagine two plates separated by only a few hundred nanometers, less than the wavelength of visible light. At that scale, the quantum fluctuations excluded between the plates are noticeably different from those allowed outside. The imbalance creates a pressure that can be measured with precision instruments. The force may be small, equivalent to only a few piconewtons for plates of typical size, but its existence confirms that the vacuum is not passive. It can move matter. It can push. That is a remarkable conclusion to draw about nothing. The Casimir effect has also found relevance beyond pure theory. In the field of nanotechnology, for example, where devices operate at extremely small scales, Casimir forces can play a role in how components behave. Tiny mechanical parts can stick together or resist separation because of these vacuum-induced pressures. Engineers must account for this when designing microelectromechanical systems. In this way, the vacuum's subtle influence moves from the realm of abstract physics into practical engineering. Nothing once again shows its hand in the tangible world. There are variations of the Casimir effect as well. For instance, if one uses different materials, such as dielectric plates rather than perfect conductors, the strength and even the direction of the force can change. Under some conditions, repulsive Casimir forces have been predicted and observed. This suggests that the vacuum's influence is versatile, dependent on the properties of the materials and the geometry of the configuration. The effect is not a one-size-fits-all phenomenon, but a rich interplay between quantum fluctuations and boundary conditions. The Casimir effect also connects to other areas of physics, including cosmology. The basic principle that restricting modes of quantum fields alters the vacuum energy parallels the way cosmologists think about the universe as a whole. If boundary conditions on small scales can create measurable forces, what happens when the boundary is the entire cosmos? The concept of vacuum energy driving cosmic acceleration is, in some sense, a grand version of the same principle. The details differ, but the underlying theme is that the vacuum is never neutral. It responds to constraints, it exerts influence, and it shapes the world in ways both small and large. This raises fascinating questions about the nature of reality. If the vacuum can push on plates in a laboratory, might it also play a role in the origin and fate of the universe? Could the same principle that brings two nanometer-scale objects together also be related to the force that accelerates galaxies apart on cosmic scales? The parallels are not perfect, but the connection is suggestive. Both point to the vacuum as an active agent in physics, not a silent background. There's also a philosophical dimension to this. For centuries, thinkers debated whether nothing could exist. Some argued that emptiness was impossible, that space must always be filled with substance. Others, like Newton, insisted that empty space was real and fundamental. The Casimir effect adds a new twist. It shows that what we call empty space is filled with fluctuations that have real consequences. In some sense, both sides of the old debate were partly right. There is emptiness in the sense of no ordinary matter, but there is also presence in the form of quantum fluctuations. The vacuum is a strange hybrid, a state that defies simple categorization. When we step back and look at the bigger picture, the Casimir effect illustrates a recurring theme in physics, that the simplest concepts often turn out to be the most deceptive. Emptiness, which seems so straightforward in everyday language, conceals layers of complexity. The vacuum, which sounds like absence, turns out to be a sea of restless energy, and forces that appear only in the abstract mathematics of field theory turn out to be measurable in the laboratory. Nothing becomes something, and that something can push. Experiments continue to probe the Casimir effect in new ways. Improved techniques allow for measurements with increasing precision, testing predictions of quantum field theory, and searching for deviations that might hint at new physics. Some experiments explore Casimir forces at different temperatures, geometries, or material configurations, hoping to uncover subtleties that expand our understanding of the vacuum. Each refinement strengthens the conclusion: the vacuum is active, structured, and indispensable to our understanding of the world. The story of the Casimir effect also highlights the interplay between theory and experiment in physics. Casimir's original prediction was rooted in the mathematics of quantum electrodynamics, but it took decades before technology advanced enough to test it. The eventual confirmation reinforced not only the theory, but also the broader framework of quantum field theory. It demonstrated that the counterintuitive predictions of the theory were not abstract games but accurate descriptions of reality. It is tempting to ask whether effects like this mean that the vacuum can be manipulated, whether its energy can be harnessed. Popular speculation sometimes imagines using vacuum forces for propulsion or energy extraction. But as with zero-point energy more generally, the uniformity of the vacuum and the laws of thermodynamics make such ideas impractical. The Casimir effect is real, but it does not provide a free source of power. Its importance lies in what it teaches us about the nature of emptiness, not in what it offers as a technology. Still, the fact that the vacuum can push remains one of the most striking demonstrations of quantum reality. It confirms that the world is not built on a neutral background but on an active stage. The vacuum shapes what happens, even when it looks like nothing is there. It is this lesson, more than any practical application, that gives the Casimir effect its enduring importance. As we continue deeper into the story, the focus will shift from how the vacuum pushes on plates in a laboratory to how it pushes on the universe itself. Because if empty space can influence matter at nanometer scales, it can also influence the cosmos at the larger scales. The same restless background that nudges two plates together may be driving the acceleration of galaxies apart. Nothing, once again, refuses to stay still. By the end of the 20th century, physicists had grown comfortable with the idea that the vacuum was not truly empty. Quantum field theory had shown that fluctuations were always present, that zero-point energy was unavoidable, and that experiments like the Casimir effect proved these ideas in tangible ways. But the story of nothing took yet another unexpected turn when cosmologists looked at the larger scales of the universe. Observation suggested that the expansion of the cosmos was not slowing down, as many had expected, but accelerating. Something in the fabric of space itself was acting like a repulsive force, pushing galaxies apart faster and faster as time passed. The best explanation is that vacuum energy, on cosmic scales, is responsible, and when physicists speak of dark energy, they are often referring to this same mysterious phenomenon, the energy of nothing accelerating everything. To set the stage, consider what was expected before this discovery. After Edwin Hubble showed in the 1920s that galaxies are receding from one another, the idea of an expanding universe became central to cosmology. Gravity, however, was thought to work against this expansion. Every galaxy's mass should attract every other, gradually slowing the expansion down. Some theorists even imagined that the universe might eventually reverse course, collapsing back into a big crunch. The balance between expansion and gravity seemed to depend on the density of matter in the cosmos, but in the late 1990s, two teams of astronomers set out to measure this balance using distant supernovae as cosmic markers. These supernovae, known as Type Ia, explode with consistent brightness, making them useful as standard candles to gauge distances. By comparing their apparent brightness with their redshift, astronomers could infer how the expansion of the universe had changed over time. To their surprise, the data showed that the expansion was not slowing down. Instead, it was speeding up. The farther away the supernova, the faster the universe seemed to be stretching. This discovery shocked the scientific community and earned the teams the Nobel Prize in Physics in 2011. The simplest explanation for this acceleration is that empty space itself carries an energy density, a vacuum energy that does not dilute as the universe expands. Unlike matter or radiation, which become less dense as space stretches, vacuum energy remains constant. This means that as the universe grows, the influence of vacuum energy becomes more and more dominant. On small scales, its effects are imperceptible. On cosmic scales, over billions of years, it drives acceleration. Nothing in this picture becomes the engine of the universe's future. This idea is closely tied to Einstein's cosmological constant. When Einstein first developed general relativity, his equation suggested that the universe should not be static. It should either expand or contract. But at the time, most astronomers believed the cosmos was eternal and unchanging. To reconcile his equations with that view, Einstein added a term to his theory, the cosmological constant, which acted like a repulsive force in spacetime counterbalancing gravity. Later, when Hubble discovered that the universe was expanding, Einstein abandoned the constant, reportedly calling it his greatest blunder. But decades later, the accelerating expansion revived the cosmological constant as a natural explanation. It seems that Einstein's discarded idea was closer to the truth than anyone imagined. In modern terms, the cosmological constant can be understood as the energy density of the vacuum, a constant contribution to the stress energy of the universe. It is the simplest form of dark energy, requiring no exotic fields or complicated mechanisms. Observations so far are consistent with this simple picture, though alternative models exist. Some propose that dark energy might be a dynamic field, slowly changing over time rather than a constant. Others explore whether modifications to gravity itself could mimic the effects. But the cosmological constant remains the leading candidate, not least because it emerges naturally from the idea of zero-point energy. And here lies a profound puzzle. When physicists calculate the expected vacuum energy from quantum field theory, the result is vastly larger than what observations suggest. The calculated value exceeds the measured value by an almost incomprehensible factor, often cited as 10^-20, the largest known discrepancy between theory and experiment in all of science. This mismatch is the vacuum catastrophe, the cosmological constant problem. It tells us that while we know vacuum energy is real, we do not yet understand how it is tamed or reduced to the small value that drives cosmic acceleration. This problem sits at the intersection of quantum physics and cosmology, making it one of the deepest unsolved questions in science. Some physicists suspect that unknown symmetries cancel out most of the vacuum energy, leaving only a tiny residue. Others suggest that new physics beyond our current theories may be at work, perhaps linked to quantum gravity or to ideas about the multiverse. In some versions of string theory, for example, different possible universes can have different vacuum energies, and we happen to live in one where the value is small enough for galaxies, stars, and life to exist. Whether this is a satisfying explanation or not is debated, but it underscores how perplexing the question is. What makes the situation even more striking is that dark energy dominates the present universe. Roughly 70% of the total energy density of the cosmos is in this form. Ordinary matter, the stuff of stars, planets and people, makes up only a few percent. Dark matter adds about a quarter, but the lion's share belongs to the energy of empty space. The universe, in other words, is mostly made of nothing, and that nothing controls its destiny. This has consequences for the future. If dark energy is truly a cosmological constant, then the universe will continue expanding forever, with galaxies drifting farther and farther apart until distant ones fade from view. Eventually, observers in the far future may see only their local cluster of galaxies, with the rest of the universe hidden beyond a horizon. The cosmic web that we map today will dissolve into isolation, shaped by the relentless acceleration of vacuum energy. Nothing will dominate everything. But if dark energy evolves over time, the future could be stranger still. Some models predict that if the energy density grows stronger, the universe could end in a big rip, where galaxies, stars, planets, and even atoms are torn apart by runaway expansion. Other models suggest that dark energy might decay, allowing expansion to slow or reverse. Each possibility depends on the true nature of vacuum energy, a question we cannot yet answer. The fate of the cosmos hangs on the properties of nothing. To study this mysterious force, astronomers are conducting ever more detailed surveys of the sky. They measure the distribution of galaxies, the behavior of galaxy clusters, the bending of light by large-scale structures, and the subtle imprints left on the cosmic microwave background. Each of these observations helps refine our understanding of dark energy. While the evidence strongly supports its existence, the details remain elusive. We know it is there, we know it accelerates the universe, but we do not know exactly what it is. This state of affairs has a peculiar resonance with history. Centuries ago, philosophers debated whether nothing could exist at all. Newton and Descartes argued about whether space was an independent entity or inseparable from matter. Now, modern physics tells us that empty space not only exists, but dominates the cosmos. And yet, even as we accept this, we remain uncertain about its nature. The old debates continue in new forms, transformed by observation and mathematics, but still circling the same enigma. The idea that nothing accelerates the universe also challenges our intuition in another way. Normally, when we think of motion or change, we imagine forces arising from tangible things, pushes, pulls, collisions, exchanges. To suggest that acceleration comes from the very emptiness of space defies that picture. It is as though the stage on which the play unfolds has become an actor in its own right, driving the action forward. Nothing has become a cause. From a technical standpoint, vacuum energy fits neatly into Einstein's equations. The cosmological constant acts like a uniform pressure, one that does not clump or dilute but remains constant everywhere. But from a conceptual standpoint, it raises profound questions. Why does empty space have energy at all? Why is the value small but not zero? What does this energy say about the link between quantum fields and space-time geometry? Each of these questions points toward physics we do not yet understand. Despite the uncertainties, the discovery that nothing accelerates the universe has reshaped cosmology. It has forced scientists to rethink the composition of the cosmos, to recognize that what we once thought of as absence is now the dominant presence. It has linked the smallest scales of quantum fluctuations to the largest scales of cosmic expansion. And it has reminded us that the mysteries of nothingness are not abstract musings, but measurable realities. The vacuum, with its zero-point energy and fluctuations, exerts forces in the laboratory, nudges plates together in the Casimir effect, shifts energy levels in atoms, and now, on the grandest scale, drives galaxies apart. the same principles that operate in the smallest spaces between metal plates echo across the cosmos, shaping its history and future. Nothing connects the microscopic to the cosmic, binding the story of atoms to the story of galaxies. As research continues, the next steps may come from both directions, from precision experiments probing the vacuum at small scales, and from astronomical surveys mapping the universe at the largest. Each approach tackles the same mystery from a different angle. Together they may bring us closer to understanding how nothing can accelerate everything, how the quiet background of the vacuum can set the rhythm of the cosmos itself. When Einstein completed the general theory of relativity in 1915, he had reimagined space and time as a single dynamic fabric, one that could bend and curve under the influence of mass and energy. The equations he wrote to describe this fabric were elegant and powerful, capable of explaining planetary orbits, the bending of light, and even predicting entirely new phenomena. But as Einstein explored the cosmological implications of his equations, he faced a troubling realization. His mathematics suggested that the universe could not be static. It wanted to expand or contract. At the time, the prevailing belief among astronomers was that the universe was eternal and unchanging, a static cosmos without beginning or end. This belief was deeply ingrained, not only scientifically, but philosophically. A dynamic universe seemed too radical. To reconcile his equations with the accepted wisdom, Einstein introduced an additional term, one that could act as a counterbalance to gravity. This was the cosmological constant, a mathematical addition that provided a repulsive force spread uniformly through space. Gravity, left to itself, would pull matter together and eventually collapse the universe. The cosmological constant, by contrast, pushed outward, resisting this collapse. By carefully adjusting its value, Einstein could produce a universe that remained static, poised in balance between attraction and repulsion. For him, this was a compromise, a way to preserve the beauty of his equations while aligning them with the expectations of astronomers. The constant was not plucked from thin air. It fit naturally within the framework of general relativity. The field equations relate the curvature of spacetime to the distribution of energy and momentum. Adding a constant term on the geometric side of the equation was mathematically simple and consistent. It acted like a uniform energy density of the vacuum, filling all of space equally. Nothing in the structure of the theory forbade it. Einstein justified it as a necessary modification, a way to stabilize the cosmos. For several years, the cosmological constant sat quietly in the theory, not widely questioned. But in the 1920s, evidence began to emerge that the universe was not static after all. The work of Vesto Melvin Slipher and later Edwin Hubble showed that distant galaxies are moving away from us. Their light shifted toward the red end of the spectrum. The recession was not random. It followed a clear pattern. The farther away a galaxy was, the faster it receded. This suggested that space itself was expanding. Einstein's reaction to this discovery is legendary. When confronted with the evidence of cosmic expansion, he reportedly abandoned the cosmological constant, declaring it unnecessary. According to one famous anecdote, he called it the biggest blunder of his life, a misguided attempt to force his theory into alignment with the static model of the universe that turned out to be wrong. Whether he actually used those exact words is debated, but the sentiment was clear. He regretted introducing the term, and for decades afterward, many physicists avoided it, treating it as a relic of a mistaken era. Ironically, the cosmological constant would eventually return, not as a mistake, but as a central piece of modern cosmology. The discovery of cosmic acceleration in the late 1990s breathed new life into Einstein's discarded term. The simplest way to explain the acceleration was to reintroduce the constant, interpreting it as vacuum energy. What Einstein had once viewed as a blunder now seemed prescient. He had stumbled in his effort to stabilize the universe onto an idea that captured one of the most profound truths of the cosmos. that empty space itself has energy. The dual history of the cosmological constant illustrates the strange path of science. At one moment it seemed like an unnecessary artifice, an embarrassment. At another it became the leading explanation for the most important discovery in cosmology of the 20th century. Its story reveals how concepts in physics can shift in meaning depending on the context, how ideas discarded in one era can be revived in another, and how the boundary between mistake and insight is not always clear. To see why the constant works as an explanation for cosmic acceleration, it helps to consider how it acts within relativity. The equations of general relativity describe how spacetime curves in response to the distribution of mass and energy. The cosmological constant adds a term that behaves like a uniform energy density, one that does not dilute as the universe expands. Its pressure is negative, meaning it acts as a repulsive force. This negative pressure drives acceleration, counteracting gravity on large scales. In the language of cosmology, it produces an equation of state with a parameter value of -1, a simple but powerful description. The connection to vacuum energy emerges naturally from quantum theory. As we've seen, quantum fields never reach absolute silence. Even in their ground states, fluctuations remain, and those fluctuations contribute energy. This energy is uniform, filling all of space equally, and thus looks exactly like a cosmological constant when plugged into Einstein's equations. The identification seems almost unavoidable. Vacuum energy and the cosmological constant appear to be two faces of the same coin, but here we encounter the problem again. The theoretical predictions of vacuum energy's magnitude are staggeringly larger than what observations show. Quantum field theory suggests that the vacuum should have a density of energy far higher than what is required to explain cosmic acceleration. Observations indicate that the constant is real but incredibly small compared to those calculations. This mismatch, the vacuum catastrophe, remains unsolved. The cosmological constant both explains the data and challenges our understanding at the deepest level. Over the years, physicists have proposed various ways to resolve the puzzle. Some suggest that symmetries cancel most of the vacuum energy, leaving only a tiny residue. Others look to ideas beyond the standard model of particle physics, hoping that new particles or fields might balance out the energy. Still others explore the possibility that our universe is only one of many, and that the value of the constant varies across them. In such a multiverse scenario, we happen to live in a region where the constant is small enough to allow galaxies and life. Whether this is a satisfying explanation or a last resort is hotly debated, but it shows how seriously the problem is taken. The cosmological constant is not only a theoretical curiosity, it shapes the destiny of the cosmos. If it remains constant in time, then the universe will continue accelerating indefinitely. Galaxies will drift farther and farther apart until, from any given point, the rest of the universe slips beyond the cosmic horizon. Stars will burn out, galaxies will fade, and the night sky will empty as acceleration isolates every observer in their own cosmic bubble. The long-term fate of everything is tied to the value of this constant. If, on the other hand, the constant is not truly constant, if it evolves or decays, the future could be different. Cosmologists study these possibilities carefully, looking for any signs of deviation from a pure constant. So far, the data align closely with Einstein's original term. But the question remains open, and it is one of the most active areas of research in physics today. Each new survey of galaxies, each new measurement of cosmic background radiation, is another attempt to pin down the true nature of this mysterious term that Einstein once regretted. Looking back, one can appreciate the irony of Einstein's blunder. By adding the constant, he anticipated the idea that space itself has energy. By discarding it, he aligned with the discovery of expansion. In both cases, his choices shaped the course of physics, and in both cases the underlying idea refused to disappear. The cosmological constant stands as a reminder that even mistakes in science can contain profound insights. that ideas may lie dormant for decades only to return as central truths. The cosmological constant also illustrates how nothing can become one of the most important players in physics. What was introduced as a mathematical adjustment to preserve a static cosmos has become the key to understanding the universe's acceleration. It shows that nothingness, far from being irrelevant, can dominate the behavior of everything. The lesson is humbling. Even the greatest physicist of the 20th century misjudged the role of his own invention, and yet the invention itself continues to guide us. As the story unfolds, the cosmological constant leads naturally into broader questions about the origin of the universe. If vacuum energy fills space, could it have sparked the beginning? Could fluctuations in this energy have triggered inflation, the rapid expansion that set the stage for everything we see today? These questions remind us that the line between cosmic history and cosmic destiny runs straight through the heart of nothingness, through the constant that Einstein once tried to discard. When we follow the thread of physics all the way back through time, we eventually arrive at the most puzzling question of all: how did the universe begin? The discovery of cosmic expansion tells us that the universe has not always existed in its present form. If it is expanding now, then in the past it must have been smaller, denser, and hotter. Extrapolate far enough, and you reach a state where all the matter, all the energy, and even the fabric of space itself are compressed into an initial condition. This picture is what we call the Big Bang. It is not an explosion in space, as it is sometimes described in popular accounts, but an expansion of space itself carrying everything with it. The natural question that arises is whether this beginning came from nothing, or whether some deeper reality lies beneath it. The earliest hints of a beginning came from both observation and theory. In the 1920s, Georges Lemaitre, a Belgian priest and physicist, suggested that the universe began as a primeval atom, an initial state that expanded into the cosmos we see today. His idea was not immediately accepted. Many scientists preferred models that avoided a beginning altogether, such as the steady-state theory, which proposed that matter was continuously created as the universe expanded, keeping its density constant over time. A beginning seemed unsettling, raising philosophical and even theological implications that physicists were hesitant to embrace. But as observations accumulated, the evidence for a hot, dense origin grew stronger. The most decisive came in the 1960s, when Arno Penzias and Robert Wilson discovered the cosmic microwave background, the faint afterglow of radiation left over from the early universe. This discovery confirmed that the cosmos had once been in a hot, dense state, filled with radiation that has since cooled as space expanded. With this evidence, the Big Bang became the leading model of cosmic origins. Yet the Big Bang model raises its own profound questions. If the universe began from an initial state, what was that state? Was it truly nothing, or was it something else, compressed beyond our current understanding? Physics alone cannot yet give a final answer, but it does provide a framework for exploring the possibilities. One possibility is that the universe did indeed emerge from nothing, if by nothing we mean the absence of space, time, matter, and energy. In this view, the Big Bang was not an event that happened in space, but the event that brought space and time into existence. Asking what happened before the Big Bang may therefore be meaningless, since before requires time, and time itself may not have existed. In this sense, the universe could be said to have arisen from nothing, but whether this is truly nothing, or whether it is a form of something deeper, is an open question. Quantum mechanics provides another angle. In quantum theory, fluctuations are unavoidable. Even a vacuum is never truly empty. Some cosmologists suggest that the universe could have originated from a quantum fluctuation, a spontaneous event where a small patch of space appeared and then expanded. Normally, such fluctuations vanish quickly, returning to the vacuum. But if one fluctuation triggered a runaway process called inflation, it could grow into an entire universe. In this scenario, the cosmos as we know it began as a fluctuation of nothing. Inflation is a powerful idea. It proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent exponential expansion, growing unimaginably fast. This solves several puzzles. It explains why the universe appears so uniform on large scales, why it is nearly flat, and why it contains the right kinds of seeds for galaxies to form. Inflation takes the quantum fluctuations of the vacuum and magnifies them, stretching them to cosmic scales. The galaxies and clusters we see today may trace their origins to these tiny disturbances in nothingness. But inflation raises further questions. What caused it to begin? What field drove it? How did it end? These remain subjects of intense research. Some models suggest that inflation may not have been a one-time event but an ongoing process, producing multiple universes in a vast multiverse. If so, our universe may be just one bubble among many, each with its own properties, each arising from fluctuations of a larger vacuum. In this picture, nothing gives rise not only to something but to many somethings, endlessly. Another perspective comes from attempts to merge quantum mechanics with general relativity. In quantum gravity, the distinction between space, time, and matter may break down. The Planck scale, where both quantum effects and gravitational effects are equally strong, is the frontier where our current theories fail. At this scale, the concept of space-time itself may be emergent, not fundamental. If space-time is not fundamental, then what lies beneath it? Could the universe have emerged from a pre-geometric state, a kind of nothing that is not the absence of existence but the absence of space-time as we know it? These are ideas physicists are still struggling to understand. The question of whether the universe came from nothing also has a philosophical dimension. What do we mean by nothing? If we define it as the absence of particles, then quantum fluctuations show that something can emerge. If we define it as the absence of space-time itself, then the Big Bang may represent the origin of both. But if we define it as absolute non-existence, with no laws, no structure, no possibility, then the question becomes more difficult. How could anything, even a fluctuation, arise from absolute non-existence? Some argue that in physics, we never deal with absolute nothing. The nothing of science is always a structured state, whether it is a vacuum, a field, or a pre-geometric condition. Absolute nothing may be beyond the reach of physics altogether. Despite these challenges, the Big Bang model has given us remarkable insights. It tells us that the universe has a finite age, about 13.8 billion years. It tells us that space and time themselves are dynamic, stretching and evolving. It tells us that matter, energy, and even the elements that make up our bodies were forged in cosmic history. Whether or not the ultimate origin was nothing, the fact that the universe had a beginning remains one of the most profound discoveries of modern science. When we think of beginnings, it is tempting to imagine a singular moment, a sharp boundary between nothing and something. But physics suggests that the boundary may not be so clear. The universe may have passed through phases, from a quantum foam to inflation to the hot Big Bang, each stage building on the previous. The idea of a single moment of creation may be replaced by a more nuanced picture, where nothingness gradually gives way to structure. There are models that attempt to avoid a beginning altogether. Cyclic models propose that the universe undergoes endless cycles of expansion and contraction. In these scenarios, the Big Bang was not the beginning but the latest bounce in an eternal sequence. Other models, such as the ekpyrotic scenario, suggest that our universe emerged from the collision of higher dimensional branes in a larger multiverse. In such views, there may never have been nothing in the absolute sense. Instead, our universe was born from processes in a deeper, larger reality. Still, the mystery remains. Whether we imagine the universe emerging from a quantum fluctuation, a multiverse, a pre-geometric state, or a cycle, we are still left with the question of why there is something rather than nothing. Why do the laws of physics exist at all? Why is there a vacuum in which fluctuations can occur? These questions may be beyond the scope of science, or they may one day find answers in a deeper theory. For now, they remain at the edge of knowledge, a reminder of how elusive the concept of nothing truly is. What we can say is that the universe as we know it did not arise from nothing in the everyday sense. It did not emerge from an empty void like an object pulled out of a hat. Instead, it seems to have emerged from conditions where the usual categories of space, time, and matter do not apply. These conditions may be described as nothing compared to our familiar world, but they are still something in the language of physics. The Big Bang marks the boundary where our current understanding begins, but what lies on the other side is still a mystery. This makes the origin of the universe one of the most profound and unsettled questions in science. It ties together cosmology, quantum physics, relativity, and philosophy. It reminds us that our language struggles to capture the true nature of nothingness, and it shows that even in the most advanced theories, the concept of nothing remains slippery, never quite yielding to definition. The study of the cosmic microwave background, the search for primordial gravitational waves, the exploration of quantum gravity, all of these efforts aim to push our understanding further back, closer to the beginning. Each step reveals more about the history of the cosmos, but each step also raises deeper questions. When cosmologists trace the history of the universe back to its earliest moments, they encounter a puzzle. The Big Bang model describes a universe that was once hot and dense, expanding and cooling to form the structures we see today. But if we take that model on its own, it leaves certain questions unanswered. Why does the universe appear so uniform in every direction, even across regions that should never have been in contact with one another? Why is space so nearly flat, neither strongly curved like a sphere nor wildly open like a saddle? And where did the tiny irregularities come from that later grew into galaxies and clusters? In the late 1970s and early 1980s, a new idea emerged that offered answers to all of these puzzles at once. This idea is known as cosmic inflation. It proposes that in the first fraction of a second after the Big Bang, the universe underwent a phase of exponential expansion, growing by an enormous factor in an unimaginably short time. During this brief era, space itself stretched so rapidly that regions once close together were carried far apart, and the seeds of cosmic structure were imprinted on the fabric of space-time. The remarkable feature of this theory is that it takes the quantum fluctuations of the vacuum, the restless energy of nothing, and magnifies them to cosmic scales. In this way, quantum nothing shaped everything. The basic picture begins with a hypothetical field, often called the inflaton. In quantum field theory, every kind of particle is associated with a field, and the inflaton is a field that dominated the energy of the universe in its earliest moments. Unlike ordinary matter or radiation, which dilute as space expands, the energy stored in the inflaton field can remain nearly constant. This constant energy density behaves like a cosmological constant, driving exponential expansion. While the inflaton field sat in a state of high energy, space expanded at a staggering rate, doubling in size again and again in tiny fractions of a second. To grasp the scale, imagine that the universe expanded by a factor of at least 10 Tlol 26 in less than 10 Davro 32 seconds. Distances smaller than an atom ballooned to astronomical scales almost instantly. This expansion smoothed out any irregularities, explaining why the universe appears so uniform today. Regions that had once been in causal contact, able to exchange information, were stretched beyond each other's horizons, giving rise to the observed uniformity across the sky. At the same time, the exponential growth flattened the geometry of space, ironing out any curvature and leaving the cosmos nearly flat on large scales. But inflation did more than solve these puzzles. It also provided a natural origin for the small fluctuations that later became galaxies. The quantum vacuum is never still. Even during inflation, the inflaton field experienced quantum fluctuations. Normally, such fluctuations are microscopic, confined to subatomic scales. But inflation stretched them, magnifying them to cosmic proportions. As inflation ended and the universe transitioned into the hot Big Bang phase, these fluctuations became imprinted as tiny variations in density. Over billions of years, gravity amplified them, pulling matter into clumps that became galaxies, stars, and planets. The cosmic web of structure that we map with telescopes today may trace its roots to quantum noise from nothingness. Evidence for this comes from the cosmic microwave background, the faint afterglow of radiation from about 380,000 years after the Big Bang. High-precision measurements such as those from the WMAP and Planck satellites reveal minute temperature variations across the sky, on the order of 1 part in 100,000. These variations match the statistical patterns predicted by inflation. The fluctuations are nearly scale invariant, meaning they look similar across a wide range of sizes, just as inflation predicts. They are also almost, but not perfectly Gaussian, another feature consistent with quantum fluctuations. The match between theory and observation is one of the strongest pieces of evidence in favour of inflation. Yet, as powerful as the idea is, inflation is not without mysteries. What is the nature of the inflaton field? What potential energy landscape did it follow? How exactly did inflation end? And how did its energy convert into the hot plasma of the early universe? These questions remain open, driving ongoing research. The basic framework of inflation is widely accepted, but its details are still debated. Different models predict different signatures, some of which may be testable with future observations. One of the most intriguing predictions is the existence of primordial gravitational waves, ripples in spacetime generated during inflation. These waves would leave a distinctive pattern in the polarization of the cosmic microwave background. Detecting such a signal would provide strong confirmation of inflation and open a window onto physics at energies far beyond what particle accelerators can reach. Several experiments such as BICEP and the South Pole Telescope have searched for this signature, and while no definitive detection has yet been made, the quest continues. The discovery of primordial gravitational waves would be a breakthrough, linking the smallest quantum fluctuations to the largest scales of the cosmos. The concept of inflation also raises questions about the global structure of the universe. In some models, inflation does not end everywhere at once. Instead, it ends in patches, creating bubble universes within a larger inflating space. Our observable universe could be just one bubble among many, each with different properties. This leads to the idea of eternal inflation, where the process never completely stops but continues generating new universes indefinitely. If this is true, then the multiverse is a natural consequence of inflation, and the vacuum fluctuations of one bubble may be mirrored by countless others. Such ideas stretch the boundaries of science, but they flow naturally from the mathematics of inflation. They also tie back to the theme that nothing is never truly nothing. In the context of inflation, the quantum vacuum is not a passive void, but an active medium, one that can drive expansion, create structure, and perhaps spawn entire universes. The very existence of galaxies and stars may depend on the unavoidable jitters of the vacuum. Without fluctuations, inflation would have produced a perfectly smooth cosmos, featureless and lifeless. It is the imperfections, born of quantum uncertainty, that gave rise to everything we know. Another striking aspect is how inflation connects the physics of the very small to the physics of the very large. Quantum field theory describes the microscopic world of particles and interactions. General relativity describes the macroscopic world of gravity and spacetime. Inflation sits at the intersection, requiring both to explain the cosmos. It shows that the vacuum, a concept born in the quantum domain, has consequences for the structure of the universe as a whole. The bridge between the Planck scale and the cosmic horizon is built on the restless energy of nothing. Critics of inflation point out that while it solves many problems, it also raises new ones. The lack of direct detection of primordial gravitational waves, the difficulty of identifying the inflaton, and the possibility of eternal inflation leading to a multiverse all complicate the picture. Some argue that inflation may be less inevitable than its proponents claim, and alternative models of the early universe have been proposed. These include bouncing cosmologies, in which a previous universe collapsed and rebounded, and emergent models, in which the universe existed in a quasi-static state before transitioning to expansion. Each of these alternatives seeks to address the same puzzles as inflation, but none has matched its explanatory power or its agreement with observation. Even if refinements or replacements emerge, the central lesson of inflation remains compelling. Quantum fluctuations, magnified to cosmic scales, can shape the destiny of the universe. Nothing is not inert but fertile, capable of seeding galaxies, stars, and ultimately life. The idea that the largest structures in existence trace their origin to the tiniest disturbances in the vacuum is one of the most astonishing insights of modern physics. The pursuit of inflationary physics continues, with new experiments, new observations, and new theoretical models. Future telescopes may measure the cosmic microwave background with even greater precision, searching for subtle signatures of inflation. Gravitational wave detectors may one day catch the faint echoes of the early universe. Advances in particle physics may shed light on the fields that drove inflation. Each step brings us closer to understanding how quantum nothing shaped everything. When we speak of places where nothingness takes on its most extreme form, black holes stand at the centre of the discussion. They are regions where matter collapses so completely that the usual fabric of space and time is warped beyond recognition. In the everyday world, even the densest objects we encounter, mountains, stars, or even neutron stars, still consist of matter with volume and structure. Black holes are different. They represent a collapse so complete that the concept of ordinary matter no longer applies. They are places where the question of what emptiness really means is pushed to its breaking point. The idea of a black hole was not born with Einstein, though relativity gave it its modern form. As early as the late 18th century, John Michel in England and Pierre-Simon Laplace in France speculated about dark stars, objects so massive that even light could not escape their gravity. These ideas were largely forgotten because Newtonian gravity could not fully capture what happens when collapse goes to extremes. It was Einstein's general relativity, published in 1915, that provided the framework to describe such objects properly. Almost immediately afterward, Karl Schwarzschild found a solution to Einstein's equations that described the space-time around a spherically symmetric, non-rotating mass. This solution revealed the possibility of a boundary, later called the event horizon, from which nothing, not even light, can escape. At first, this solution seemed like a mathematical oddity rather than a physical reality. Many physicists, including Einstein himself, doubted that nature would permit such extreme objects to form. But as the decades passed, evidence grew. Observations of massive compact objects in space, the detection of X-ray emissions from binary systems, and, more recently, the imaging of black hole shadows and the detection of gravitational waves from black hole mergers have confirmed that black holes are real. They are not curiosities of the equations, but inhabitants of our universe, sculpting galaxies and influencing cosmic evolution. What makes black holes so extraordinary is the way they challenge our understanding of nothing. Inside the event horizon, space and time swap roles. The inward direction becomes as inevitable as time's forward march. No matter what path you take, you are carried toward the singularity, the central point where densities become infinite, and the curvature of space-time diverges. At this singularity, the known laws of physics break down. Whether it is truly a point of infinite density or whether some new physics takes over is an open question. What we can say is that the ordinary categories of matter, space, and even emptiness lose their meaning there. The singularity is a place where our concepts fail. The event horizon itself is not a physical surface in the traditional sense. It is a boundary defined by geometry, the point of no return. From the outside, a black hole appears dark because light cannot escape its pull. But the horizon is not a wall. It is a region where escape becomes impossible. To an outside observer, anything approaching the horizon appears to slow down, time stretching out indefinitely as light is redshifted to invisibility. To the falling object itself, crossing the horizon feels uneventful. It passes through without noticing anything special, at least until tidal forces become overwhelming deeper inside. This duality, where the horizon is both ordinary and extraordinary, illustrates how black holes force us to rethink the meaning of emptiness. The space-time around a black hole is also remarkable. It is not merely curved, it is warped to extremes. Light can orbit a black hole in a circular path at a radius called the photon sphere. Matter falling inward accelerates to enormous speeds, releasing tremendous energy as it spirals toward the horizon. In astrophysical settings, this process produces some of the most luminous phenomena in the universe, such as quasars and active galactic nuclei. These brilliant beacons are powered not by matter colliding with other matter, but by matter interacting with curved emptiness, giving up energy as it falls into a region from which there is no escape. The role of black holes in galaxies adds another layer. Observations show that nearly every large galaxy harbours a supermassive black hole at its centre, with masses millions or billions of times that of the Sun. These black holes influence the motion of stars around them, and their activity regulates the growth of galaxies. In a sense, the nothing at the centre of a galaxy helps shape everything else. The void of the event horizon becomes a controlling factor in cosmic architecture. Black holes also highlight the tension between relativity and quantum mechanics. According to general relativity, once matter crosses the horizon, it is lost to the outside world forever. But in the 1970s, Stephen Hawking showed that quantum effects allow black holes to radiate. This radiation arises from vacuum fluctuations near the horizon, where pairs of virtual particles can form. Normally such pairs annihilate quickly, but near the horizon, one particle may fall in while the other escapes. To an external observer, the escaping particle appears as real radiation. Over time, this process allows a black hole to lose mass and eventually evaporate. Hawking's insight revealed that black holes are not truly black. They glow faintly, not from their interiors but from the restless activity of the vacuum itself. This discovery deepened the connection between black holes and nothingness. It showed that even the darkest regions of the universe are not free from quantum fluctuations. It also raised the infamous information paradox. If black holes evaporate completely, what happens to the information about the matter that fell in? Does it vanish, violating the principles of quantum mechanics, or is it somehow preserved? This paradox remains one of the most important open questions in theoretical physics, pointing toward the need for a theory that unites relativity and quantum mechanics. The information paradox illustrates once again how black holes bring us to the edge of understanding. They are not just astrophysical objects, but laboratories for fundamental physics. They force us to confront the limits of our theories, to ask whether space-time is continuous or whether it has a deeper quantum structure. They force us to reconsider the meaning of nothing, since what appears as emptiness may conceal vast amounts of hidden information. Even observationally, black holes reveal how emptiness can take form. The Event Horizon Telescope collaboration in 2019 produced the first image of a black hole's shadow in the galaxy M87. The image showed a dark central region surrounded by a glowing ring of hot gas, light bent by extreme gravity. The shadow is not a direct view of the event horizon, but a silhouette cast by curved space-time. It is an image of nothing, shaped by the most intense warping of space we can observe. To capture it, scientists combined telescopes across the Earth, creating a planet-sized observatory. The achievement confirmed predictions of relativity, and provided a direct glimpse of how nothingness looks when space itself collapses inward. Gravitational wave astronomy adds another dimension. Since 2015, detectors like LIGO and Virgo have observed the ripples in space-time produced by colliding black holes. These signals match the predictions of general relativity with extraordinary precision. They show that when black holes merge, space-time itself rings like a bell, radiating energy across the cosmos. Once again, nothing becomes dynamic. The collisions do not emit light or matter, but pure distortions of the vacuum, travelling at the speed of light across billions of years. Detecting these waves confirms that the geometry of emptiness is not static, but alive with motion when stirred by extremes. The study of black holes continues to evolve, with new questions arising at every turn. What happens at the singularity? Does spacetime truly end, or is it replaced by a new kind of structure at the Planck scale? Are black holes gateways to other regions of the universe, as some speculative ideas propose? Could they even connect to other universes in a multiverse? These questions remain speculative, but they highlight how black holes act as touchstones for our understanding of nothing. They push our theories to their limits and beyond. In practical terms, black holes also remind us that nothingness is not a passive absence. The event horizon is empty in the sense that nothing escapes it, yet its influence governs the behaviour of matter and light around it. The singularity is beyond our description, yet it defines the fate of everything that crosses the horizon. Even the radiation that escapes from a black hole is not a product of the hole itself, but of the vacuum fluctuations near its boundary. Emptiness, at every step, proves to be an active force. As we study black holes more deeply, we find that they are not isolated curiosities but central to cosmic history. They regulate galaxies, shape the distribution of matter, and test the laws of physics. They are extreme manifestations of relativity, and they expose the quantum nature of the vacuum. They are the places where space itself disappears, and where nothing takes on its most paradoxical form. If black holes radiate through quantum fluctuations, what does that say about the vacuum energy on cosmic scales? If spacetime curves to infinity at a singularity, what does that say about the structure of nothing at the Planck length? When black holes first emerged as serious candidates in astrophysics, they were imagined as regions from which nothing could ever escape. Their defining feature, the event horizon, was thought to be absolute. Light could not get out, matter could not get out, and once something crossed that boundary, it was gone forever. This picture seemed consistent with general relativity, which describes gravity as the curvature of spacetime. In Einstein's framework, the horizon is a one-way surface. For decades, physicists assumed that this was the end of the story, but in the 1970s, Stephen Hawking demonstrated that the story was not so simple. When quantum mechanics is added to the picture, black holes are no longer perfectly black. They glow, albeit faintly, by emitting radiation. This result, now called Hawking radiation, transformed our understanding of black holes and reshaped the discussion of nothingness. The basic idea begins with the recognition that the vacuum is never empty. Quantum field theory insists that even in regions devoid of particles, fluctuations are constantly taking place. These fluctuations can be described as pairs of virtual particles, one with positive energy and one with negative energy, that appear together and then annihilate, leaving no trace. In most circumstances, these pairs are transient and unobservable, but near the event horizon of a black hole, the situation changes. Imagine such a particle pair forming right at the edge of the horizon. Normally, the two particles would collide and disappear almost instantly. But if the pair forms in the right place, one particle can fall into the black hole while the other escapes. The one that falls in effectively reduces the mass of the black hole, while the one that escapes carries energy away. To an outside observer, it appears as though the black hole is radiating particles. Over enormous timescales, this process can cause the black hole to lose mass and eventually evaporate entirely. This picture is a simplified way to describe a more complex calculation. Hawking's original derivation involved applying quantum field theory to curved spacetime, analysing how the presence of the horizon changes the vacuum state. The mathematics shows that the vacuum near a black hole is not the same as the vacuum far away. Observers at infinity detect a flux of particles with a thermal spectrum, as if the black hole has a temperature. This temperature depends inversely on the black hole's mass, The smaller the black hole, the hotter it is. For a stellar mass black hole, the temperature is tiny, only billionths of a degree above absolute zero. For a supermassive black hole, the temperature is even smaller, but for a microscopic black hole, the radiation could be intense. The implications are staggering. Black holes, once thought to be eternal, have finite lifetimes. A black hole with the mass of the Sun would take far longer than the age of the universe to evaporate, but in principle, the process is inevitable. Over unimaginable timescales, black holes radiate their mass away, leaving behind only the faint hiss of quantum fluctuations turned into real particles. Nothingness itself is the source of this radiation. The discovery also raises deep questions about the nature of information. According to quantum mechanics, information about a physical system is never lost. But if a black hole evaporates completely, what happens to the information about the matter that fell in? Does it disappear, violating the principles of quantum theory, or is it somehow encoded in the radiation? This is the information paradox, one of the most famous unresolved problems in theoretical physics. For decades, it has been a central puzzle, driving research into the nature of spacetime, quantum gravity, and the foundations of physics. Different ideas have been proposed. Some suggest that the information is truly lost, requiring a revision of quantum mechanics. Others argue that it must be preserved, perhaps encoded in subtle correlations in the radiation. Still others explore the possibility that the horizon itself stores information, like a hologram. This led to the holographic principle, the idea that the information content of a region of space can be described by degrees of freedom on its boundary. While no final answer has been reached, the paradox shows how Hawking's discovery opened a door to new thinking about nothingness. The thermal nature of Hawking radiation also connects black holes to thermodynamics. Long before Hawking's work, Jacob Bekenstein had argued that black holes should have entropy proportional to the area of their event horizons. Entropy, in thermodynamics, measures the number of possible microscopic configurations consistent with a system's macroscopic state. For ordinary matter, entropy is tied to disorder and heat. For black holes, Bekenstein proposed that entropy is tied to the horizon's area, suggesting that black holes are the most entropic objects in the universe. Hawking's calculation confirmed this by showing that black holes emit thermal radiation at a temperature consistent with the laws of thermodynamics. Together, these results establish the laws of black hole mechanics, which parallel the ordinary laws of thermodynamics but applied to horizons. This realization strengthened the connection between gravity, quantum mechanics, and thermodynamics, three pillars of physics that normally operate in separate domains. In black holes, they converge. The vacuum fluctuations that give rise to radiation link the quantum world to the curvature of spacetime. The thermal spectrum links them to entropy and temperature. Nothingness once again proves to be fertile, generating not only particles but connections between the deepest principles of nature. Hawking's insight also has practical consequences in cosmology. If black holes evaporate, then the ultimate fate of the universe is different from what was once imagined. After stars burn out and galaxies fade, black holes may remain as the final objects. But given enough time, vastly more than the current age of the universe, they too will evaporate. The cosmos will not end with eternal black holes, but with the radiation of nothingness itself. The universe, in the far future, may be filled only with faint radiation, the last whisper of black holes dissolving into the vacuum. There are speculative possibilities as well. Some have suggested that microscopic black holes, if they formed in the early universe, might have evaporated by now, producing bursts of radiation. Detecting such signals could provide evidence of physics beyond the standard model. Others wonder whether Hawking radiation could be harnessed as a power source, though the temperatures required are far beyond practical reach for any black holes we can create or observe. These speculations remain on the edge, but they reflect the profound impact of the idea that emptiness itself can radiate. The paradoxes surrounding Hawking radiation continue to inspire new approaches. String theory, loop quantum gravity, and other attempts at quantum gravity often take the information problem as a testing ground. The holographic principle, developed from these debates, has become a powerful idea in theoretical physics with applications far beyond black holes. It suggests that space-time itself may be an emergent phenomenon, arising from more fundamental degrees of freedom. In this sense, Hawking's discovery may have pointed toward the deepest structure of reality. Even observationally, there is ongoing interest. Direct detection of Hawking radiation from astrophysical black holes is impossible with current technology, since the signal is drowned out by other sources. But analog systems in laboratories, such as fluids, Bose-Einstein condensates, and optical systems, can mimic aspects of black hole horizons. In some of these systems, radiation resembling Hawking's prediction has been observed, providing indirect support. While these are not black holes in the literal sense, they show that the physics of horizons and fluctuations is robust, appearing in diverse contexts. Hawking's result also reshaped how we think about the vacuum. Normally, radiation is associated with matter. A hot object glows because its atoms are vibrating. A star shines because nuclear reactions release energy. But in Hawking radiation, no matter is involved in the emission. The radiation comes from the vacuum itself, altered by the presence of the horizon. In this way, nothingness acts like a source of light. It blurs the line between absence and presence, between void and substance. The broader significance is that Hawking radiation ties together ideas that once seemed unrelated. The quantum vacuum, curved spacetime, entropy and thermodynamics all converge at the horizon. This convergence hints that the ultimate theory of physics, whatever it is, must unify these domains. Black holes, by turning nothingness into light, act as gateways to that deeper theory. If horizons radiate because of vacuum fluctuations, then perhaps the entire universe, with its cosmic horizon, may be subject to similar principles. The connection between black holes and cosmology, between Hawking's discovery and dark energy, remains one of the most intriguing frontiers. Nothingness, once again, proves not to be empty, but to be the engine of some of the most profound mysteries we face. When quantum field theory matured in the middle of the 20th century, physicists began to realize that the restless vacuum carried an enormous consequence. Each quantum field, whether it describes electrons, photons, quarks, or any other particle, has a ground state, and in that ground state there is zero-point energy. On its own, one such contribution might seem small, but when all possible modes of all fields are added up, the total energy of the vacuum becomes immense. At first, this was treated as a technical detail, something to be swept aside with the hope that it would cancel out. But when cosmology entered the picture, the issue could no longer be ignored. The vacuum energy had gravitational consequences, and the numbers produced by theory did not agree with what was observed. The mismatch was not just a small error. It was the largest known discrepancy between theory and experiment in the history of physics. This problem came to be known as the vacuum catastrophe. To understand how it arises, consider how energy works in quantum field theory. Each mode of a field behaves like a harmonic oscillator, and each oscillator retains half a quantum of energy even in its lowest state. Summing over all modes leads to a divergent result, an infinite energy density. Physicists develop techniques such as renormalization to subtract infinities and make sense of calculations. These methods work beautifully for predicting measurable quantities like particle interactions, producing answers that agree with experiments to many decimal places. But when it comes to the vacuum energy itself, renormalization cannot simply ignore the problem. Gravity couples to all forms of energy, including the vacuums. The energy of nothing contributes to the curvature of space-time. And so the question became unavoidable. How much energy does the vacuum really have? Calculations produced a staggering figure. Depending on the cutoff scale used, the predicted vacuum energy density exceeded the observed value by factors of 10^60 to 10^120. To put this in perspective, it is as if theory predicted that the ocean should rise to the height of a mountain range, while observation showed it lapping gently at the shore. This is not the kind of error that can be fixed by adjusting a parameter slightly. It is an error so enormous that it suggests something is profoundly missing from our understanding. Observationally, the vacuum energy reveals itself through the acceleration of the universe. As discovered in the late 1990s, distant supernovae show that cosmic expansion is speeding up. The simplest explanation is a cosmological constant, equivalent to vacuum energy with a small positive value. This means the vacuum does contribute to the dynamics of the cosmos, but only slightly. The actual value required to fit the data is tiny compared to the theoretical prediction. That gap is the catastrophe. Why do the contributions of quantum fields not add up to the colossal value expected? Some have proposed that different fields cancel one another. For example, in supersymmetry, every particle has a partner with opposite statistics, and their vacuum contributions can offset each other. In exact supersymmetry, these cancellations would be perfect, yielding zero vacuum energy. But supersymmetry, if it exists, must be broken at the energies we observe, and so the cancellation would not be complete. Supersymmetry might reduce the discrepancy but not eliminate it entirely. Others suggest that the answer lies in quantum gravity, a theory not yet complete. At the Planck scale, where both quantum mechanics and general relativity are equally strong, the structure of spacetime itself may alter how vacuum energy behaves. Perhaps the naive summation of modes is not valid at such scales, and a deeper theory will provide a natural cutoff. But without a full theory of quantum gravity, this remains speculation. Another line of thought appeals to the multiverse. In some versions of string theory, there are many possible vacuum states, each with its own value of vacuum energy. If countless universes exist, each with different constants of nature, then we happen to live in one where the vacuum energy is small enough to permit galaxies, stars, and life. This anthropic reasoning is controversial. Some physicists accept it as the least unlikely explanation, while others reject it as unsatisfying, preferring a dynamical or symmetry-based solution. Either way, it shows the lengths to which researchers will go to reconcile theory and reality. The vacuum catastrophe is more than a mismatch of numbers. It is a clash between two pillars of modern physics. Quantum field theory, the framework of the microscopic world, says the vacuum should be enormously energetic. General relativity, the framework of the macroscopic world, says the vacuum's energy curves space-time. An observation shows that curvature is tiny. Bridging this gulf requires a unification of the two theories, something physicists have sought for decades. The failure to resolve the catastrophe highlights the incompleteness of our current understanding. To see how dramatic the problem is, consider the cosmological constant in practical terms. The observed value corresponds to an energy density of about 10 to 9 joules per cubic meter. That is small, less than the energy contained in a single light bulb spread over an entire room. But the predicted value from quantum theory is more like 10 to 113 joules per cubic meter. The gap between these two numbers is so vast that it defies intuition. It is not just a missing decimal point, but an abyss. Some physicists argue that the catastrophe is a clue, pointing the way toward new physics. Just as the ultraviolet catastrophe in classical physics led to quantum mechanics, perhaps the vacuum catastrophe will lead to a deeper synthesis of quantum theory and gravity. Others caution that progress may be slow, requiring not only new mathematics, but also new kinds of experiments to probe regimes far beyond current reach. The challenge is formidable, but the potential rewards are equally great. Meanwhile, cosmologists continue to measure the effects of dark energy with increasing precision. Observations of the cosmic microwave background, galaxy clustering, and gravitational lensing all confirm that the acceleration is real and consistent with a cosmological constant. If deviations from constancy were found, it might point to a dynamic form of dark energy rather than a true constant. That could provide clues about the underlying physics. So far, however, the evidence points stubbornly to a simple constant value. Nothingness appears to be uniform and unchanging, at least on cosmic scales. Laboratory experiments also probe aspects of the vacuum. Precision measurements of the Casimir effect, atomic energy levels, and particle interactions all reveal the presence of vacuum fluctuations. These effects confirm that zero-point energy is real in the quantum sense. The paradox arises only when gravity is included. Without gravity, the vacuum energy can be shifted or subtracted without consequence. With gravity, it cannot be ignored. The catastrophe is the collision of two otherwise successful theories. The history of physics suggests that such collisions often herald revolutions. When classical mechanics clashed with the behavior of atoms, quantum mechanics was born. When Newtonian gravity clashed with the speed of light, relativity emerged. Perhaps the vacuum catastrophe is the modern equivalent, the signal that a new framework is needed. Some dream that it will lead to a quantum theory of gravity, unifying the large and the small. Others hope it will reveal hidden symmetries that balance the books of energy. Whatever the resolution, it will likely transform our understanding of nothing. In the meantime, physicists work with what they have. The cosmological constant is treated as a parameter, adjusted to fit observations. Calculations proceed as though the vacuum energy can be ignored for most purposes because its effects are small on laboratory scales. This pragmatic approach allows science to progress, even while the deeper problem remains unresolved. It is a reminder that physics often advances in stages, patching over difficulties until a more complete theory emerges. The vacuum catastrophe also highlights how the simplest ideas can become the most challenging. Emptiness, once thought to be trivial, turns out to conceal the greatest mismatch in all of science. The attempt to quantify nothing has produced numbers so vast that they threaten to overwhelm our theories, and yet this very mismatch keeps the search alive. It forces scientists to ask whether our picture of the vacuum is incomplete, whether spacetime itself is emergent, whether the concept of nothing needs to be redefined once again. Particle accelerators, precision cosmology, gravitational wave detectors, and quantum technologies all push the boundaries of what can be measured. Each advance may provide hints, however subtle, about the true nature of the vacuum, and each hint may guide us toward resolving the clash between theory and reality. For now, the vacuum catastrophe remains one of the deepest puzzles, a reminder that even in the heart of nothing lies one of the greatest mysteries of all. As the study of inflation, quantum fluctuations, and vacuum energy unfolded, physicists began to entertain an idea that stretches the imagination to its limit. If our universe could arise from quantum nothing, if inflation can take a small patch of space and stretch it into an entire cosmos, then perhaps this process does not happen just once. Perhaps it happens many times, endlessly, in ways that produce not a single universe, but a vast collection of universes. This idea, known as the multiverse, suggests that what we call the universe may be only a bubble in a much larger reality. In this picture, nothing does not simply give rise to something. It gives rise to infinite somethings. The seeds of this idea lie in inflation itself. In many models of inflation, the field that drives the rapid expansion does not decay everywhere at once. Instead, in some regions, inflation ends and the hot Big Bang begins, creating a bubble universe like our own. But in other regions, inflation continues, pushing space to expand even more. This process can go on forever, with bubbles forming within an eternally inflating background. Each bubble becomes a universe in its own right, potentially with different physical constants, different laws, even different numbers of dimensions. From the perspective of the multiverse, our observable universe is just one small part of an unending cosmic foam. This scenario, known as eternal inflation, is not the only path to the multiverse. String theory, one of the leading candidates for a theory of quantum gravity, also suggests a landscape of possibilities. The equations of string theory allow for an enormous number of possible vacuum states, each corresponding to a different way that extra dimensions could be compactified or shaped. Each vacuum state leads to a different set of physical constants, particle properties, and forces. The number of possible states is sometimes estimated at 10^500 or more. If inflation can populate these states, then each one could correspond to a different universe. In this sense, the multiverse may be a natural consequence of fundamental physics. The idea is radical, but not without precedent. Throughout history, our cosmic perspective has expanded. The Earth was once thought to be the centre of everything. Then it became one planet among many. The Sun, once imagined as the hub of the cosmos, was revealed to be an ordinary star in a galaxy of hundreds of billions. That galaxy turned out to be just one among countless others. Each step has widened our horizon, showing us that what we thought was everything was only a part. The multiverse is the next step in this progression, suggesting that even the universe itself may not be all there is. If true, the multiverse would help explain one of the most puzzling features of our universe: why the constants of nature take the values they do. The strength of gravity, the charge of the electron, the mass of the proton, the value of the cosmological constant. These numbers seem finely tuned to allow for the existence of complex structures like stars, planets, and life. In the multiverse picture, this fine-tuning is no mystery. If countless universes exist with different constants, then it is not surprising that we find ourselves in one where the constants permit life. Observers can only exist in such universes. This reasoning is called the Anthropic principle. While controversial, it provides one possible answer to the question of why our universe seems so improbably suited for complexity. Of course, the multiverse raises as many questions as it answers. The first and most pressing is whether it can ever be tested. Science relies on observation and experiment, and by definition other universes are beyond our horizon. If they are forever causally disconnected from us, then how can we know they exist? Some argue that indirect evidence may be possible. For example, if two bubble universes collide, the imprint of the collision might be visible in the cosmic microwave background as a subtle anomaly. Others suggest that statistical predictions can be made. If the multiverse is real, then certain distributions of constants should be more common than others, and our universe should reflect that distribution. But for now, the evidence remains circumstantial, and the multiverse sits at the edge of science, part physics, and part philosophy. Another challenge is the measure problem. If infinitely many universes exist, how do we assign probabilities? How do we count which kinds of universes are more common? Without a well-defined measure, predictions become ambiguous. Physicists debate how to define probabilities in an infinite multiverse, but no consensus has been reached. This difficulty underscores how far we are from turning the multiverse into a fully testable theory. Yet the idea persists because it seems to follow naturally from theories we already take seriously. Inflation, supported by observations of the cosmic microwave background, leads to eternal inflation in many models. String theory, developed to unify gravity with quantum mechanics, leads to a vast landscape of vacua. The multiverse may not be a separate invention, but a consequence of the tools we use to describe reality. It emerges not from speculation alone, but from attempts to solve existing problems. The multiverse also reshapes the concept of nothingness. If universes can arise from quantum fluctuations of a vacuum, and if that vacuum itself is part of a larger inflating background, then nothingness becomes a fertile ground for endless creation. Each bubble universe begins as a fluctuation, expanding into a cosmos with its own laws. Nothing gives rise not to a single something, but to an infinity of them. The distinction between absence and presence blurs when nothing becomes a generator of everything. This raises philosophical questions as well. If the multiverse exists, then what is the meaning of laws of nature? Are they universal, applying everywhere, or are they local, applying only within each bubble? If the latter, then what we call the laws of physics may be more like environmental conditions, one set among many possibilities. The multiverse would mean that there is no single necessity behind the structure of reality, only a vast diversity. Our universe, with its particular constants, would be a local expression, not a universal truth. Such ideas challenge the traditional goals of physics. For centuries, scientists have sought a single, elegant set of laws that describe everything. The multiverse suggests that this dream may be misplaced. Instead of one unique theory, there may be a vast landscape of possibilities, with our universe being one realization among countless others. For some, this is unsatisfying, even unsettling. For others, it is liberating, a recognition that reality is richer than we imagined. Speculative as it is, the multiverse also connects to deeper questions about origins. If universes can arise from fluctuations of the vacuum, then perhaps the multiverse itself has no beginning. Inflation could be eternal, producing new universes endlessly into the future and endlessly into the past. Or perhaps the multiverse had an origin of its own, a deeper layer of reality we cannot yet see. These questions stretch our imagination, but they follow naturally once we accept that nothing can give rise to something. If one universe can emerge, why not many? From a practical standpoint, the multiverse continues to motivate research. Cosmologists search for subtle signs of bubble collisions in the microwave background. String theorists explore the landscape of vacua, seeking to understand its structure and its implications. Philosophers of science debate whether the multiverse counts as science at all, or whether it slips into metaphysics. The discussions are lively, reflecting both the promise and the challenge of the idea. In the end, the multiverse remains an open possibility. It may be real, or it may be an artifact of incomplete theories. It may be testable someday, or it may remain forever beyond our reach. But even as a hypothesis, it changes how we think about nothing. What once seemed like emptiness now looks like the soil of infinity, capable of sprouting endless universes. Nothing becomes not only something, but everything, repeated without end across a boundless reality. If the vacuum can generate universes, is space-time itself fundamental, or is it an emergent phenomenon? Could nothingness be not the absence of space-time, but the foundation from which space-time itself arises? When general relativity and quantum mechanics are each taken on their own terms, they describe the world with remarkable success. Relativity explains the geometry of space-time, the behavior of planets, the bending of light, the expansion of the universe, and the warping of black holes. Quantum mechanics, along with its extension into quantum field theory, explains the microscopic world of atoms, particles, forces, and fluctuations. Each theory is precise, predictive, and confirmed by countless experiments. But when the two are brought together, when we try to apply both to the same extreme conditions, contradictions arise. Gravity resists quantization, and quantum theory resists being curved into space-time. Nowhere is this clash more evident than in the concept of nothing. The vacuum, which already confounds us with its fluctuations and energy, becomes even more puzzling when the geometry of space-time itself is subject to quantum uncertainty. In general relativity, the vacuum is defined by geometry. Empty space is described by solutions to Einstein's equations with no matter present. These solutions are smooth and continuous, with space-time behaving like a fabric that can bend, stretch, or ripple. Even when no particles are present, space-time itself is still there, a real entity that shapes and is shaped by energy. In quantum field theory, by contrast, the vacuum is the lowest energy state of fields. It is not smooth or continuous, but restless and fluctuating. In isolation, each picture works, but together they generate contradictions. Does the vacuum curve spacetime according to its enormous predicted energy, or does it not? How can spacetime itself be quantized when the very notion of geometry is classical? Quantum gravity is the name given to the attempt to resolve these questions. It is not one specific theory, but a broad category of efforts to unify relativity and quantum mechanics. Within this pursuit lie some of the most ambitious frameworks in physics: string theory, loop quantum gravity, causal dynamical triangulations, emergent spacetime models, and more. Each of these tries to answer the same basic question: what is the nature of nothing when spacetime itself is quantum? String theory approaches the problem by replacing point particles with tiny vibrating strings. In this picture, the vacuum is not a simple background, but a configuration of strings and higher dimensional objects. Different vibrations give rise to different particles, and the geometry of extra dimensions determines the forces and constants of nature. The vacuum energy, in this context, depends on the shape of these extra dimensions. String theory suggests a vast landscape of possible vacua, each corresponding to a different universe. The problem of nothing becomes the problem of selecting which vacuum we inhabit out of a near infinite number of possibilities. Loop quantum gravity takes a different path. It quantizes space-time itself, treating geometry as built from discrete units, much like atoms make up matter. In this framework, space is woven from loops, networks of quantized connections. The smooth fabric of relativity emerges only as an approximation at large scales. At the smaller scales, space-time is granular. The vacuum here is not continuous emptiness, but a network of discrete building blocks. Nothing becomes a lattice of geometry, a foundation that is fundamentally quantum. Other approaches imagine that space-time may not be fundamental at all. Instead, it could be emergent, like temperature or pressure, arising from deeper microscopic degrees of freedom. In these models, the vacuum is not the bottom of space-time, but the ground state of something more basic. This perspective is inspired by hints such as the thermodynamic properties of black holes, which suggest that space-time behaves like a system with entropy and temperature. If entropy and temperature are emergent properties, then perhaps space-time itself is emergent too. In this view, nothing may be not the absence of space-time, but the hidden microstructure from which space-time emerges. Each of these attempts reshapes the concept of nothing in a different way. In string theory, nothing is a vacuum defined by the configuration of extra dimensions. In loop quantum gravity, nothing is a network of discrete quanta. In emergent models, nothing is the hidden substrate beneath space-time. All of them challenge the classical idea that nothing is simply emptiness. Instead, they suggest that nothing may be as structured and complex as something. One of the deepest puzzles quantum gravity seeks to address is the information paradox. Black holes, as described by Hawking radiation, appear to destroy information, contradicting quantum mechanics. Resolving this paradox requires a quantum description of space-time, one that can account for both radiation and information. Some proposals suggest that information is stored on the horizon, encoded holographically. Others propose that space-time is entangled, that quantum entanglement itself builds the geometry. In either case, the paradox forces us to confront the vacuum at its most extreme. The nothingness of a black hole's interior is not simple absence, but a test bed for the deepest principles of physics. The Planck scale, where quantum gravity becomes essential, defines the boundary of our knowledge. At scales of about 10 to 35 meters and 10 to 44 seconds, both quantum uncertainty and gravitational curvature dominate. Here, space-time may fluctuate violently, producing a frothy, quantum foam. This foam is a far cry from classical emptiness. It is a seething, dynamic sea where geometry itself appears and disappears, where nothing is turbulent. Trying to describe this foam is one of the central challenges of quantum gravity, Some models suggest that wormholes may spontaneously form and vanish within this foam, tiny bridges connecting different regions of spacetime. Others propose that spacetime is threaded with topological fluctuations, knots and twists that constantly reconfigure. These possibilities are speculative, but they underscore the point. At the smallest scales, nothing is not still. It is active, complex, and perhaps creative. The very geometry of reality may emerge from this chaotic sea. The pursuit of quantum gravity is motivated not only by theoretical desire, but also by necessity. The vacuum catastrophe, the information paradox, the early universe, and the structure of singularities all demand a quantum description of space-time. Without it, our theories remain incomplete. Nothingness, far from being trivial, is the place where our knowledge collapses. Understanding nothing is therefore synonymous with understanding everything. The search continues with a combination of mathematics, thought experiments, and indirect evidence. Particle accelerators probe high energies, though still far below the Planck scale. Observatories map the cosmos, looking for subtle signatures that might hint at quantum gravity, such as imprints in the cosmic microwave background or deviations in gravitational waves. Laboratory experiments test the limits of quantum mechanics in ever larger systems, hoping to glimpse the interface with gravity. Each effort is a small step toward answering the question of what nothing really is. The philosophical implications are as striking as the physical ones. If space-time is emergent, then what we experience as the void is not a primary reality, but a secondary appearance. The deepest nothing may be something else entirely, a set of underlying rules or structures that we cannot yet see. This forces us to reconsider what we mean by existence, what we mean by emptiness, and what we mean by reality. The boundary between something and nothing blurs, just as it has at every stage of physics. The effort to unify relativity and quantum mechanics continues to challenge and inspire. Some believe the answer will come from a breakthrough in mathematics, a new framework as radical as quantum mechanics was a century ago. Others believe it will come from observations, from phenomena that cannot be explained without quantum gravity. Whatever the path, the problem of nothing remains central. It is not an abstract question but a concrete challenge, embedded in the heart of our most successful theories. In this way, quantum gravity and the problem of nothing are inseparable. To describe the vacuum at the smallest scales, to explain the energy that accelerates the universe, to resolve the paradoxes of black holes, we must understand what nothing really is. And that understanding may require letting go of the idea that nothing is absence. It may mean embracing the idea that nothing is structure, fluctuation, or emergence. It may mean that the concept of emptiness, as we intuitively understand it, has no place in the final theory of reality. In the study of physics, the concept of entropy occupies a special place. It is a measure of disorder, of the number of microscopic configurations consistent with a system's macroscopic state. It tells us how energy is distributed, how systems evolve, and why certain processes are irreversible. The second law of thermodynamics, which states that entropy tends to increase, is one of the most fundamental principles in science. It explains why heat flows from hot objects to cold ones, why gas spreads to fill a container, why eggs do not unscramble, and why time has a direction. Entropy gives time its arrow, and when applied to the universe as a whole, entropy points toward a future of growing disorder, culminating in a state sometimes called the heat death. In that far-off epoch, the universe will reach a condition of maximum entropy, a condition that resembles nothingness more than anything we can imagine. To understand how this future comes about, it helps to start with the present. The universe today is rich with structure. Stars burn brightly, converting nuclear fuel into heat and light. Galaxies swirl, powered by gravity pulling matter into vast clusters. Planets orbit, atmospheres circulate, and on at least one world complex life thrives. All of this structure exists because entropy is not yet maximized. There are gradients of temperature, pressure, and density. Energy flows from one place to another, driving processes that build complexity. But the second law insists that over time these gradients will diminish. Energy will spread out, becoming more evenly distributed. Differences will fade. Order will give way to disorder. The fate of stars provides a clear example. Stars shine by fusing lighter elements into heavier ones, releasing energy in the process. But fusion cannot continue forever. Eventually, stars exhaust their nuclear fuel. Small stars cool into white dwarfs, slowly fading over trillions of years. Larger stars end more violently, exploding as supernovae and leaving behind neutron stars or black holes. In each case, the organized process of fusion gives way to inert remnants. As more stars burn out, the universe loses sources of concentrated energy. The flow of usable energy diminishes and entropy increases. Galaxies too evolve. Over immense timescales, gravitational interactions can eject stars from galaxies, or cause galaxies to merge. Black holes at galactic centers grow as they consume matter, locking energy behind their horizons. The cosmic dance continues, but the overall trend is toward greater entropy. Stars fade, gas disperses, and galaxies lose their vibrancy. Eventually, the night sky will darken as fewer stars remain. Black holes themselves represent the highest entropy objects in the universe. According to Bekenstein and Hawking, a black hole's entropy is proportional to the area of its horizon. For a supermassive black hole, this entropy is enormous, dwarfing that of ordinary matter. In a sense, black holes are entropy factories, swallowing matter and increasing the disorder of the cosmos. But even black holes do not last forever. Through Hawking radiation, they slowly evaporate, releasing their mass back into the universe as faint radiation. Over unimaginable timescales, 10 years, 100 years or more, black holes will vanish, leaving only diffuse energy behind. What remains after the last black hole evaporates is a universe filled with low-energy particles and radiation. The energy is spread thin, nearly uniform. Temperatures approach absolute zero. No gradients remain to drive processes. With no differences in temperature or density, no work can be done. Entropy has reached its maximum, and the universe has entered heat death. This state is not dramatic like a fiery apocalypse or a cosmic collapse. It is quiet, featureless, and eternal. Nothing happens because nothing can happen. The concept of heat death was first proposed in the 19th century, when scientists realized that the second law of thermodynamics applied not only to engines and laboratories but also to the cosmos itself. It was a startling idea that the universe, once vibrant with activity, might eventually settle into stillness. For a long time, this was treated as speculation, since the age and fate of the universe were poorly understood. But with modern cosmology, the concept has gained new weight. Observations of cosmic expansion, dark energy, and black hole physics suggest that heat death may indeed be the ultimate destiny. Dark energy plays a crucial role in shaping this fate. Because the expansion of the universe is accelerating, galaxies are moving away from each other faster and faster. Over time, most galaxies will disappear beyond our cosmic horizon, receding so quickly that their light can never reach us. The observable universe will shrink to a small local region, isolated from the rest. Eventually, even that region will fade as stars die and black holes evaporate. Acceleration hastens the isolation, ensuring that the flow of energy becomes ever more diluted. Entropy also ties into the arrow of time. The reason we perceive time as moving forward is that entropy increases. In a universe headed toward heat death, the arrow of time points inexorably toward a state of nothing happening. Some physicists even speculate that once maximum entropy is reached, time itself may lose its meaning. Without change, without processes, the distinction between past and future may dissolve. In this sense, heat death is not only the end of activity, but perhaps the end of time. There are alternative scenarios. If dark energy is not constant but changes over time, the future could be different. A stronger dark energy could cause a big rip, tearing apart galaxies, stars, and even atoms. A weaker dark energy could allow expansion to slow or reverse, leading to a big crunch. But if dark energy remains constant, as current data suggest, then heat death is the most likely outcome. The universe will not end in fire or collapse, but in the slow fading of all distinctions, the spread of energy into uniformity. From the perspective of nothingness, heat death represents a peculiar kind of emptiness. It is not the absolute nothing of no existence, but the practical nothing of no activity. Matter may still exist in some form, radiation may still drift, but nothing meaningful can occur. No structures can form, no energy can flow, no life can persist. It is a cosmos that is not absent but void of possibility. This is why physicists sometimes call it cosmic nothingness. The timescales involved are so immense that they challenge imagination. Trillions of years for stars to fade. 10D mean 40 years for protons, if they decay. 10 to 100 years for black holes to evaporate. Beyond that, perhaps 10 to 26 years or more for the last traces of activity to vanish. Compared to these spans, the current age of the universe, 13.8 billion years, is an instant. We live in the early, vibrant era of cosmic history, a brief moment when energy flows and complexity thrives. The silence of heat death lies far beyond. Still, the concept of entropy and heat death is more than speculation about the distant future. It shapes how we understand the present, the reason stars shine, the reason life exists, the reason processes occur at all is because the universe is not yet at maximum entropy. The gradients of temperature and density that drive everything are temporary imbalances, leftovers from the Big Bang and inflation. Entropy explains not only the end but the entire arc of cosmic history. It also underscores the role of nothingness in physics. Nothing is not always absolute emptiness. Sometimes it is uniformity, the absence of distinctions, the levelling of differences. Heat death is this kind of nothing, a future where the universe still exists but does not change. It is a reminder that nothingness can be approached gradually, as order dissolves into disorder, as energy spreads into stillness. The study of entropy also connects to black holes once more. Because they carry such enormous entropy, black holes dominate the entropy budget of the universe today. When they evaporate, their entropy is released into radiation, spreading disorder even further. In this way, black holes act as milestones on the road to heat death. They gather structure, then dissolve it, pushing the universe closer to uniformity. Their presence and eventual disappearance are part of the great thermodynamic story. Physicists sometimes ask whether heat death is truly the end, or whether fluctuations could create new beginnings. In a state of maximum entropy, tiny fluctuations could, in principle, produce local decreases in entropy. Over vast timescales, improbable events become possible. One such possibility is the spontaneous formation of new structures, even new universes. Another is the appearance of so-called Boltzmann brains, conscious observers arising by random fluctuation. These ideas are speculative and controversial, but they highlight how even nothingness in physics is never simple. The heat death may not be perfectly still, but punctuated by rare, random sparks. Nevertheless, the broad outline remains. Entropy increases, gradients fade, and the universe drifts towards stillness. The second law of thermodynamics, applied universally, points to this destiny. It is not a catastrophic collapse or a fiery destruction, but a quiet settling, a cosmic fading into uniformity. The arrow of time carries us there, one irreversible step at a time. When we trace the concept of nothing through the history of physics, we encounter layer after layer of redefinition. For the ancient philosophers, nothing was the absence of being. For classical physicists, nothing was empty space, a void in which particles could move. For modern physics, nothing is a vacuum filled with fluctuating fields, restless with energy. Each time we look deeper, the apparent nothingness reveals new structure. This leads to a profound question. Does physics allow for absolute nothing, the total absence of existence? Or does every attempt to define it end up producing something else? The problem begins with definition. Absolute nothing would mean no space, no time, no matter, no fields, no energy, and no laws. It would mean no framework at all within which anything could occur. But physics, by its nature, deals with things that have structure and obey rules. Even when describing a vacuum, physicists mean the lowest energy state of fields within spacetime. That is already something. The equations of quantum field theory cannot describe absolute non-existence, because their very language presumes the presence of fields and spacetime. In this sense, absolute nothing is not a concept that fits within the scientific framework. Consider the vacuum of quantum electrodynamics. To a layperson, it might be called empty space, but to a physicist it is filled with fluctuations of the electromagnetic field, with virtual photons appearing and vanishing, with corrections that shift energy levels of atoms. That is not absolute nothing. It is a structured state, with properties that can be measured. Or take the vacuum of general relativity, a solution to Einstein's equations with no matter. It is still space-time geometry, curved or flat depending on conditions. Again, not nothing but something that behaves according to laws. When cosmologists talk about the universe originating from nothing, they almost always mean from such a structured vacuum, not from absolute absence. A quantum fluctuation could produce a bubble of expanding space, but only if there is already a framework of quantum fields and laws of physics that permit such a fluctuation. The nothing in this context is more like a pre-existing sea of possibilities than true non-existence. Absolute nothing, with no laws and no possibility, could not fluctuate, could not generate a universe, could not give rise to anything. Some thinkers argue that absolute nothing is incoherent. If truly nothing existed, then no laws could exist either, and therefore no transition to something would be possible. The very fact that something exists may suggest that absolute nothing is impossible, that the minimum state of reality must contain at least some potentiality. In this view, the vacuum is the simplest possible state, but it is still something. Nothingness in the pure sense may not be allowed by physics at all. This line of reasoning intersects with the question of why there is something rather than nothing. If absolute nothing is possible, why do we not inhabit it? If it is not possible, then something exists necessarily, in some form, by the nature of logical physics. Physics can describe how universes evolve once they exist, but the question of whether absolute nothing could exist may lie outside its scope. It is not a question of equations, but of definitions. The attempts to merge quantum mechanics and relativity add further complexity. At the Planck scale, space-time may fluctuate wildly, producing a foam of geometry. This foam is sometimes described as nothing in popular accounts, but in truth, it is highly structured. It is filled with topological changes, transient connections, and quantum uncertainty. It is an arena of constant activity. Calling it nothing is misleading, though it may represent the lowest layer physics can currently describe. The very turbulence of the quantum foam shows that physics always finds something, even at the supposed foundation. Philosophers often distinguish between relative nothing and absolute nothing. Relative nothing is the absence of matter within space, the kind of nothing we encounter in a laboratory vacuum or intergalactic space. Absolute nothing is the absence of everything, including space and laws. Physics can handle relative nothing with precision. It measures vacuum fluctuations, Casimir forces, zero-point energies. But absolute nothing resists description. There is no mathematical framework for it. because mathematics itself presumes structure. Even the concept of probability presumes a system of rules. Absolute nothing admits no such system. Some physicists, when confronted with this problem, conclude that the notion of absolute nothing may be meaningless in scientific terms. Reality, they suggest, must always contain something, even if that something is only a vacuum state governed by laws. Nothing in the strictest sense may be a philosophical abstraction, not a physical possibility. In this view, the vacuum is the closest physics comes to nothing, but it is never truly nothing. It is always something else. Others attempt to push further, speculating about what might lie beyond even the vacuum. Some theories imagine that space-time is emergent, arising from deeper structures such as entanglement networks or quantum information. In these theories, what we call the vacuum is a higher-level phenomenon, emerging from more fundamental building blocks. But those building blocks are still something. The regress never reaches absolute nothing. Instead, each layer reveals another something beneath it. The multiverse idea complicates the question further. If there are many universes, each with its own laws, then absolute nothing becomes even harder to imagine. The multiverse would mean that possibility is unavoidable, that something always exists somewhere. There is no state in which there is nothing at all, only states in which there are fewer or simpler somethings. The very richness of the multiverse framework points away from absolute nothing and toward infinite variation. Even in thermodynamics, where the heat death of the universe is sometimes described as a kind of cosmic nothingness, the nothing is relative. The universe may reach maximum entropy, where no gradients remain to drive processes, but it is still filled with radiation, particles, and space-time. It is not absolute absence, but the absence of usable energy. Nothingness in this sense is not non-existence, but stillness. What emerges from all of these perspectives is that physics always finds structure, even in emptiness. The vacuum is structured by fields, by fluctuations, by laws. Space-time is structured by geometry, by curvature, by horizons. Entropy is structured by probability, by the distribution of microstates. At every level, nothing turns out to be something else. The idea of absolute nothing, stripped of laws, stripped of possibility, stripped of existence, may be a concept that physics cannot accommodate. This is not to say that the question is meaningless. On the contrary, it is one of the deepest questions we can ask, but it may not be a question physics is equipped to answer. Physics can describe the vacuum, the quantum foam, the early universe, the fate of heat death. It can measure the fluctuations of nothingness and chart the expansion of space. But whether absolute nothing can exist at all may remain outside its reach. It may be a boundary question, where physics ends and philosophy begins. Still, the pursuit of nothingness in physics has been fruitful. Each time we ask what nothing means, we discover new layers of reality. The vacuum reveals fluctuations, horizons reveal entropy, expansion reveals dark energy, quantum gravity reveals foamy geometry. Each step shows that nothing is not absence but richness. Perhaps that is the ultimate lesson, that absolute nothing is not possible, and that every attempt to describe it inevitably produces something else. When people first hear the word nothing, it feels like the simplest of all concepts. It sounds like emptiness, a blankness, the absence of all things. Yet as we have seen, when physics examines this word, it reveals a labyrinth. Every time we peel back a layer, what we thought was nothing becomes something more complicated. The void between atoms holds fields. The vacuum between galaxies carries energy. The apparent stillness of space hums with fluctuations. Even horizons and black holes, which seem like places where everything disappears, reveal information, entropy, and faint radiation born out of the restless vacuum. Nothingness, in the language of physics, refuses to be truly empty. This refusal has shaped the history of science. When Newton argued that space existed as an independent container, he he gave reality to emptiness. When Descartes denied the void, he insisted that space must be substance. Einstein then showed that spacetime is dynamic, able to stretch, bend, and ripple. Quantum field theory layered in another view, that the vacuum itself is active, with virtual particles appearing and vanishing, never resting. Each generation of physics has forced us to rethink nothing. The simple absence we imagine turns into a participant in the story, shaping forces, guiding evolution, and even determining the fate of the universe. The strangeness of nothing shows up most clearly when we try to quantify it. Calculations of vacuum energy produce numbers so large they dwarf the cosmos, yet observations show only a tiny value. Black holes reveal that horizons carry entropy and temperature, properties we normally associate with matter. Inflation suggests that fluctuations of the vacuum-seeded galaxies. Dark energy reveals that the vacuum accelerates cosmic expansion. Each of these discoveries points back to the same lesson. What appears to be empty is full of consequences. And yet, despite all this richness, the concept of absolute nothing, complete absence, without laws, without possibility, slips away. Physics has no way to describe such a state. Our theories are built on structure, whether fields, geometry, or probabilities. Even when we imagine the end of the universe in heat death, what remains is not absence but uniformity. Radiation still drifts, space-time still extends, but gradients are gone. It is a silence, not a void. The question of whether absolute nothing is possible may not belong to physics at all. It may belong to philosophy, or perhaps it is an incoherent idea altogether. Still, physics teaches us how far the investigation can go. We now know that the vacuum can push on plates in a laboratory through the Casimir effect. We know it can accelerate galaxies through dark energy. We know it can radiate from black hole horizons through Hawking radiation. We know it can shape cosmic structure through inflationary fluctuations. These are not abstractions. They are measurable, testable, and real. They show that nothing is woven into the fabric of science, not as absence but as the most subtle form of presence. The strangeness of nothing also reveals how interconnected all domains of physics have become. Cosmology relies on quantum theory to explain the early universe. Black hole thermodynamics links gravity to entropy. The vacuum catastrophe ties field theory to general relativity. The pursuit of nothing has become the pursuit of unity, because nothing sits at the intersection of every theory. In asking what emptiness means, we're really asking how the deepest principles of nature fit together. The answer, when it comes, will not only describe the void, but everything that grows from it. The persistence of nothing in physics also reshapes our sense of perspective. We're used to thinking of the world in terms of objects, stars, planets, atoms, particles. But the more we study, the more we see that what lies between objects is just as important. Empty space is not merely background, it is active and vital. The structure of galaxies, the rhythm of expansion, the stability of atoms all depend on the properties of the vacuum. In some ways, nothing is more fundamental than something. Without it, the somethings could not exist. Even the future of the universe is dictated by nothing. If dark energy remains constant, then the cosmos will expand forever, with galaxies drifting apart into unreachable silence. If entropy continues its march, then heat death will arrive, leaving a universe of stillness. These outcomes are not shaped by matter itself, but by the properties of the vacuum, by the way nothing behaves. The emptiness of space holds the destiny of all things. This recognition does not lead to despair, but to curiosity. Nothing is not simple, not trivial, not uninteresting. It is the most elusive and yet the most universal aspect of reality. It appears everywhere and hides everywhere. It challenges us to rethink language, because our words for absence cannot capture its fullness. It challenges us to rethink science, because every attempt to calculate its properties leads to contradictions, and it challenges us to rethink meaning, because what seems to be empty turns out to hold the entire fate of the cosmos. In the end, the journey through nothingness shows us how strange reality truly is. What begins as a question of emptiness becomes a question of everything. From the vacuum fluctuations in atoms to the acceleration of galaxies, from the entropy of black holes to the fate of the universe, nothing touches all scales. It links the smallest with the largest, the beginning with the end, the structure of matter with the structure of space-time. Nothing is not absence. Nothing is the hidden fabric that makes reality possible. And as we reflect on this, the story does not stop. Each new observation, each new experiment, each new theory adds another layer. The question of nothing is never finished, because physics never accepts the final word. Every solution opens another puzzle. Every apparent nothing reveals another something beneath it. The strangeness remains, and with it, the drive to keep asking. And if you've stayed with me through this long exploration, thank you for spending your time here. These late-night journeys into science are meant to keep your mind curious while letting your body rest. If you found this soothing or thought-provoking, you can support the channel by liking the video, subscribing, and letting me know what topics you'd like to hear next. I always enjoy seeing where in the world you're listening from, so feel free to share that too. For now, let the thoughts of galaxies, horizons, and the strange fullness of nothing drift quietly into the background. Settle into comfort, let your breath slow, and allow sleep to come whenever it's ready. Science will be here waiting the next time you press play. Good night.